Hello there and welcome to Science for Sleep. Where curiosity slows its breathing a little, the universe dims the lights for us, and science becomes something soft enough to drift off beside. Tonight, we're heading toward one of the strangest objects humanity has ever discovered, a place that cannot be seen directly, cannot be touched, and yet somehow became the first black hole we ever truly identified. Its name is Cygnus X1, and despite sounding like a secret military project or a particularly unfriendly robot from a 1970s film, it is actually a massive collapsed star sitting quietly in our galaxy, not especially far away in cosmic terms, patiently bending space and swallowing matter in the darkness. And perhaps the strangest part is this. Long before scientists proved black holes existed, before spacecraft and X-ray telescopes and supercomputers, people already imagined places in the universe where gravity became so powerful that not even light could escape. Which means that for centuries humanity looked up at the stars and accidentally guessed one of the most unsettling truths in physics. Not bad for a species that also invented inflatable furniture and cheese in a spray can. Still, black holes remained mostly theoretical for a very long time. Interesting equations, strange possibilities, cosmic monsters living only inside mathematics. Many scientists doubted they could actually exist in reality. Even Albert Einstein himself was uncomfortable with some of the implications. The equations of relativity allowed black holes, yes, but nature often has a habit of refusing to behave in the most dramatic way possible. And then the universe quietly produced Cygnus X1 anyway. Tonight we're going to follow the story of how humanity found it, how astronomers slowly realized something invisible was feeding on a nearby star, and why this object changed our understanding of the cosmos forever. Along the way, we'll wander through collapsing stars, warped gravity, strange radiation, and the unsettling realization that one of the galaxy's most famous black holes is, astronomically speaking, practically in our neighborhood. Which raises a slightly uncomfortable thought. What does it mean to live relatively close to something designed by physics to never let anything leave? Before we settle into that cheerful little question though, I'd love to know something simpler. Where in the world are you listening from tonight? Is it late evening where you are? Early morning? Maybe you're curled beneath blankets while rain taps softly against the window, or perhaps you're listening during a quiet train ride somewhere beneath city lights. Whatever corner of Earth you're resting in tonight, I'm very glad you're here. And if you find these sleepy journeys through science relaxing or comforting, feel free to like the video and subscribe. It helps this quiet little corner of the universe reach more wandering minds looking for somewhere peaceful to drift off for a while. Now then, let's dim the lights a bit further and travel toward a dark object hidden inside the constellation of the Swan. The constellation Cygnus has been known for thousands of years. Ancient sky watchers saw the shape of a great bird stretching across the heavens, wings spread wide through the band of the Milky Way. On clear nights, especially away from city lights, it still looks remarkably graceful, gliding overhead as though the galaxy itself were carrying it. Nothing about it suggests danger. That's the funny thing about the universe. The most terrifying objects rarely announce themselves dramatically. They don't glow red like warning signs or crack open the sky with lightning. Often, they sit quietly in ordinary places while unimaginable physics unfolds nearby. Hidden inside Cygnus is a system that looks, at first glance, like a perfectly normal bright star. In fact, for centuries, nobody had any reason to suspect otherwise. Telescopes improved, star charts became more detailed, astronomers catalogued the heavens carefully, yet the black hole remained invisible because black holes do not emit light in the usual sense. That's rather their defining personality trait. Trying to directly observe a black hole is a little like trying to photograph a hole cut into a piece of black paper during a blackout inside a cave. So how do you find something invisible? Well, you look for what it does to everything around it. That realization became one of the great turning points in modern astronomy. Scientists stopped asking, "Can we see a black hole?" and started asking, Can we see its fingerprints? Because gravity leaves fingerprints everywhere. Planets tug on stars. Stars distort gas clouds. Galaxies twist light itself. And when something enormously massive lurks nearby, the surrounding universe begins behaving strangely. In the case of Cygnus X1, the first clues arrived not through visible light, but through X-rays. Now, X-rays are peculiar things. We usually associate them with hospitals or airport scanners, or perhaps that brief moment of dread before a dentist says, "You'll feel a little pressure." But the universe produces X-rays naturally whenever matter becomes extraordinarily hot and energetic, and space, despite looking calm from Earth, is full of violent environments capable of producing them. Exploding stars release X-rays, neutron stars produce X-rays. Gas spiraling toward collapsed objects heats up so intensely that it shines in high-energy radiation invisible to human eyes. The problem is that Earth's atmosphere blocks most X-rays before they reach the ground. Convenient for life on Earth, slightly inconvenient for astronomers. So for most of human history, the X-ray universe remained completely hidden from us. The sky we thought we knew turned out to be incomplete. That changed during the 20th century when scientists finally began sending instruments above the atmosphere using rockets and satellites. Suddenly, the quiet night sky exploded into activity. Regions that looked calm in visible light were blazing violently in X-rays, and one of the brightest X-ray sources they discovered came from the direction of Cygnus, hence the name Cygnus X1. Cygnus for the constellation, X for X-rays, 1 because it was the first major X-ray source identified there, simple, efficient, slightly less dramatic than the invisible gravity beast consuming stellar material nearby, though perhaps easier to fit onto scientific paperwork. At first, astronomers weren't entirely sure what they were looking at. Space has many exotic objects capable of producing X-rays. Maybe it was a neutron star, maybe something stranger. Observations continued, measurements improved. Gradually a picture began to emerge. There appeared to be an ordinary visible star orbiting something invisible. That alone was intriguing. The visible star, now called HD 226868, is enormous, far larger and hotter than our Sun, a blue supergiant blazing with incredible energy. If placed where our Sun sits, it would utterly dominate Earth's sky, and likely remove most reasons to worry about sunscreen because the planet itself would no longer exist in recognizable form. But the truly strange part was its motion. The star was wobbling, not randomly, not chaotically. It moved as though something massive nearby was pulling on it gravitationally. Astronomers could track the motion carefully by studying shifts in the star's light spectrum. As the star moved toward Earth, its light compressed slightly. As it moved away, the light stretched. This effect, called Doppler shifting, is the same basic principle behind the changing pitch of a passing ambulance siren. Space, it turns out, behaves surprisingly like traffic sometimes. By measuring the wobble, scientists could estimate the mass of the invisible companion tugging on the star, and the numbers quickly became uncomfortable. The unseen object appeared too massive to be a neutron star. Now, neutron stars are already absurd objects. They form when massive stars collapse after supernova explosions, compressing matter so tightly that atoms themselves partially break down. A teaspoon of neutron star material would weigh billions of tons on Earth. And yet, there is a limit. Above a certain mass, even neutron degeneracy pressure cannot support the collapsed core anymore. Gravity wins completely. The object continues collapsing inward until escape velocity exceeds the speed of light. A black hole forms. The invisible companion in Cygnus X1 seemed to exceed that critical threshold, meaning there was only one known explanation left. Humanity may have finally found a real black hole. Not everyone accepted the conclusion immediately, of course. Scientists are cautious creatures by profession. Entire careers are built upon questioning dramatic claims, and black holes sounded extremely dramatic. Some researchers proposed alternative explanations. Maybe the measurements were wrong. Maybe the mass estimates were inaccurate. Maybe some unknown exotic star type existed. But observation after observation kept pointing toward the same answer. The X-rays fit the theory beautifully. Matter from the giant companion star appeared to be spiraling toward the invisible object, forming an accretion disk, a rotating whirlpool of gas heated to millions of degrees before disappearing beyond the event horizon. That process released enormous amounts of X-ray radiation. The monster could not be seen directly, but it was eating, and the universe was glowing around its mouth. There's something deeply unsettling about that image, even now. An invisible object orbiting quietly beside a bright star, feeding slowly from it over immense stretches of time. No sound, no roaring, just gravity doing exactly what gravity does, patiently. You might imagine black holes as cosmic vacuum cleaners rampaging through space, swallowing everything nearby, but reality is stranger and, oddly enough, calmer. Black holes don't hunt. They don't chase. Gravity simply shapes motion around them. If our sun were magically replaced with a black hole of equal mass, Earth would continue orbiting almost exactly as before, though admittedly the lack of sunlight would make long-term gardening somewhat challenging. What makes Cygnus X1 extraordinary isn't that it's violently devouring the galaxy. It's that it revealed black holes were real at all. Before this discovery, black holes belonged mostly to theory, interesting mathematics, exotic possibilities hidden inside relativity equations. After Cygnus X1, they became physical objects astronomers needed to study seriously. And once scientists realized black holes existed, they started finding them everywhere. Tiny stellar black holes formed from collapsing stars, giant supermassive black holes lurking at galactic centers, perhaps even intermediate black holes between the two. The universe suddenly became much darker and much stranger than humanity previously imagined, which is saying quite a lot considering we had already discovered exploding stars, neutron matter, and planets raining molten glass sideways at thousands of kilometers per hour. Astronomy rarely suffers from a lack of weirdness. Still, there's something uniquely unsettling about black holes, because they challenge our intuition so completely. Most objects in the universe eventually reveal themselves through light. Stars shine, planets reflect, nebulae glow softly. Black holes erase information from view. Cross the event horizon and nothing returns. Not matter, not signals, not light itself. The object becomes permanently disconnected from the observable universe, at least outwardly. And yet black holes also became some of the brightest objects in the cosmos indirectly, because the material around them becomes so energetic before falling inward. Entire galaxies can blaze brilliantly because their central black holes are feeding actively. It's a strange contradiction. The darkest objects can create the brightest surroundings, rather fitting perhaps for something discovered through invisible X-rays coming from an otherwise ordinary patch of sky. And through all of this, Cygnus X1 continued orbiting quietly in the constellation of the Swan, about 6,000 light-years away from Earth. Far enough that no human will ever visit it. Close enough that, astronomically speaking, it's considered relatively nearby. That phrase always sounds amusing when discussing space. Nearby in cosmic terms still means that the light reaching your eyes tonight may have left before the Roman Empire existed. Space has a wonderfully distorted sense of scale. Yet even at that distance, Cygnus X1 became one of the most important objects ever studied. It forced humanity to confront the reality that the universe contains regions where space and time behave in ways almost impossible for the human brain to visualize properly. Because black holes are not merely dense stars, they are places where geometry itself changes, where gravity curves space-time so intensely that every possible path leads inward, where clocks distort, where light bends, where, ordinary language begins struggling to keep up with physics, and perhaps that is part of why black holes fascinate us so deeply. They sit right at the border between what humans can understand and what reality actually is. We evolved to throw rocks, build fires, and occasionally forget why we walked into kitchens. Yet somehow, our species also became capable of discovering invisible collapsed stars thousands of light years away using mathematics and tiny shifts in starlight. That's honestly quite impressive, especially considering most of us still panic slightly when Wi-Fi stops working for more than 30 seconds. As the years passed, evidence for Cygnus X1 only strengthened. Better telescopes, improved measurements, more advanced X-ray observations. Eventually the scientific debate shifted from "is this really a black hole?" to "how exactly does this black hole behave?" The question was no longer whether black holes existed. The universe had answered already, and that answer opened the door to a much larger realization. If one black hole could hide beside an ordinary star within our own galaxy, how many more might be scattered silently throughout the Milky Way right now? Quite a few, as it turns out. Some isolated, some feeding actively, some drifting invisibly through space with no companion star at all. The galaxy may contain millions of stellar black holes formed from ancient dead stars. Most remain undetectable unless they interact with nearby matter strongly enough to betray their presence, which means the night sky is not merely filled with stars, it is also filled with absences, invisible wells in space-time quietly orbiting through darkness. Long before humanity discovered Cygnus X1, before satellites scanned the sky in X-rays, before physicists spoke casually about event horizons and singularities as though discussing ordinary weather patterns, the idea of a black hole existed only as a deeply uncomfortable possibility hidden inside mathematics and imagination. What's fascinating is that the concept itself is far older than most people realize. In fact, the first people to seriously imagine something like a black hole lived in a universe without radio telescopes, computers, spacecraft, or electricity. They looked at the stars with primitive instruments and somehow wandered dangerously close to one of the strangest truths in physics. The story begins in the 18th century, during a time when gravity itself was still relatively new as a scientific idea. Isaac Newton had transformed physics with his theory of universal gravitation. According to Newton, every object with mass attracted every other object with mass. Apples fell, planets orbited, the moon remained bound to Earth. Suddenly the heavens and Earth followed the same physical rules. This was revolutionary. Before Newton, the sky felt almost magical, governed by mysterious celestial principles separate from everyday life. After Newton, the universe became mechanical, predictable, mathematical, and naturally once humans discover a powerful new equation, they immediately begin asking increasingly alarming questions with it. One of those questions was surprisingly simple. What happens if gravity becomes extremely strong? At the time, scientists already understood something called escape velocity. If you throw a ball upward, Earth's gravity slows it down until it falls back. Throw it harder, and it travels higher before returning. Throw it fast enough, however, and it escapes Earth entirely. For Earth, that speed is about 11 kilometers per second. Rockets must exceed this velocity to leave the planet permanently. Now imagine increasing the mass of an object dramatically while compressing it smaller and smaller. The escape velocity rises. More gravity means a faster launch is needed to break free. Eventually, a strange possibility appears. What if the escape velocity became greater than the speed of light? That question was explored in 1783 by an English natural philosopher and clergyman named John Michell. Michell suggested that a sufficiently massive and compact star might possess gravity so powerful that even light could not escape. He called them dark stars. Now, this was an astonishingly bold idea for the 1700s. Remember, this was an era when people still travelled mostly by horse. Steam engines were primitive, the Industrial Revolution. was only beginning, and yet here was a scientist calmly proposing invisible stars capable of trapping light itself. To be fair, scientists in those days also wore wigs with a level of confidence modern society has largely abandoned, so perhaps intellectual bravery came more naturally. Still, Michel's reasoning made sense within Newtonian physics. If light behaved like tiny particles, then gravity should affect it, and if gravity became sufficiently strong, the particles of light would never escape. A few years later, the French mathematician Pierre-Simon Laplace independently proposed a similar concept. He too imagined stars so massive that light could not leave them. And then something curious happened. The idea mostly disappeared. Part of the reason was scientific uncertainty about light itself. During the 19th century, physicists increasingly understood light not as particles but as waves. Since Newtonian gravity worked best with masses and forces acting on physical objects, the idea of gravity trapping light became less convincing. Then came a deeper issue. Nobody had any evidence such objects actually existed. Dark stars sounded mathematically interesting but physically unrealistic. Astronomy at the time dealt mostly with visible objects. If something emitted no light at all, how could you possibly detect it? So the concept drifted quietly into obscurity for more than a century. Meanwhile, the universe continued behaving exactly as it pleased. Massive stars were born, massive stars died, and somewhere out there, real black holes were likely already forming, while humanity argued about whether such things were even possible. Then, in the early 20th century, everything changed again thanks to Albert Einstein. In 1915, Einstein published the general theory of relativity, one of the most important scientific achievements in human history. Instead of describing gravity as a force pulling objects together, Einstein described gravity as the curvature of space-time itself. Mass bends space-time. Objects follow those curves. What we experience as gravity is really geometry. It is an extraordinary idea when you stop and think about it. Earth is not pulling the moon in the ordinary sense. The Earth curves space-time around itself, and the moon follows the shape of that curve, rather like a marble rolling around a stretched rubber sheet. Although physicists occasionally sigh when hearing that analogy, because space-time is not literally a rubber sheet, and also because explaining relativity at parties tends to become exhausting after the third diagram on a napkin, Einstein's equations were incredibly powerful. They explained planetary motion more accurately than Newton's laws. They predicted the bending of light by gravity. They even described how time itself changes in strong gravitational fields. But hidden inside those equations was another disturbing possibility. If enough mass collapsed into a sufficiently small region, space-time could curve inward without limit. A kind of gravitational trap would form, and in 1916, only months after Einstein published general relativity, a German physicist named Karl Schwarzschild found an exact mathematical solution describing such an object. This is honestly one of the most remarkable moments in physics history. Schwarzschild solved Einstein's equations while serving on the front lines during World War I. Imagine trying to revolutionize astrophysics while surrounded by trench warfare and artillery fire. Most people struggle to answer emails under significantly calmer conditions. Schwarzschild's solution described a spherical mass compressed inside a critical radius. Beyond that boundary, space-time behaved strangely. Light could not escape outward. Paths through space-time all curved inward. Today we call that boundary the Schwarzschild radius, or more commonly the event horizon. At the time, however, nobody called it a black hole. In fact, many physicists viewed the solution as a mathematical oddity rather than a physical reality. Einstein himself doubted that nature would ever actually create such objects. And honestly, that skepticism was understandable. The equations implied something absurd, a star collapsing endlessly under its own gravity. Matter compressed beyond imagination. Space and time distorted so severely that escape became impossible. Even stranger, from an outside observer's perspective, Time near the event horizon appeared to slow dramatically due to gravitational time dilation. A falling object would seem to freeze near the edge. Light leaving the object would become redder and dimmer until it faded from visibility entirely. The physics sounded almost supernatural, and yet the mathematics stubbornly refused to disappear. Over the next few decades, physicists continued wrestling with the implications. Some believed collapsing stars might stabilize somehow before forming true black holes. Others thought unknown physical processes would intervene. Then astronomy introduced another major surprise. Stars, it turned out, are not eternal. That may sound obvious now, but for most of human history, stars seemed permanent. Fixed lights decorating the heavens forever. Modern astrophysics revealed something far more dramatic. Stars are enormous nuclear furnaces balancing gravity inward against fusion pressure outward. As long as fusion continues, the star survives, but eventually fuel runs out. And when massive stars die, gravity begins winning. In the 1930s, physicists like Subrahmanyan Chandrasekhar studied what happens to dying stars. Chandrasekhar discovered there is a mass limit beyond which white dwarf stars cannot support themselves against gravitational collapse. This was deeply controversial. Some scientists disliked the conclusion intensely because it implied catastrophic stellar collapse might genuinely happen in nature. One of Chandrasekhar's fiercest critics was Arthur Eddington, one of the era's most respected astronomers. Eddington essentially argued that nature would surely find some way to prevent such ridiculous outcomes, which is one of the more charming recurring patterns in scientific history. Humanity repeatedly says, the universe would never behave that strangely. The universe repeatedly answers, observe me. Eventually, physicists realize different stellar remnants emerge depending on mass. Smaller stars become white dwarfs. More massive stars collapse into neutron stars, and sufficiently massive stars may continue collapsing beyond even neutron degeneracy pressure. At that stage, no known force stops gravity. The star disappears behind an event horizon. A black hole forms. Still, even through the mid-20th century, many scientists remained cautious about taking black holes literally. They were mathematically allowed, yes, but perhaps impossible in practice. Then observations started becoming difficult to ignore. Astronomers discovered strange compact objects emitting powerful radiation. Radio astronomy revealed violent phenomena across the cosmos. Quasars appeared impossibly energetic. X-ray sources blazed invisibly in space. Something extraordinary was happening out there, and gradually theoretical physics and observational astronomy began converging toward the same unsettling conclusion. The universe genuinely contains collapsed objects with gravity strong enough to trap light. Around this time, the term black hole itself finally appeared. The phrase is usually credited to the American physicist John Archibald Wheeler during the 1960s. Before that, scientists used clumsier descriptions like gravitationally completely collapsed objects, which, while technically descriptive, lacks a certain conversational efficiency. Black hole captured the idea perfectly. Simple, ominous, memorable. A region of darkness from which nothing escapes. Once the name existed, public imagination seized onto it immediately. Science fiction embraced black holes enthusiastically. Writers imagined portals, cosmic abysses, gateways through time, interstellar traps. Some depictions were scientifically thoughtful. Others involved rather suspicious amounts of glowing spirals and dramatic sound effects in outer space where, inconveniently, sound cannot travel. Meanwhile, real scientists kept gathering evidence, and then came Cygnus X1. What made its discovery so important was not merely that it behaved strangely. Plenty of cosmic objects behave strangely. Space is practically organized around strange behavior. What mattered was that the numbers fit. The invisible object orbiting beside the blue supergiant star appeared too massive to be anything else known to physics. Not a white dwarf, not a... neutron star. Only a black hole remained plausible, and suddenly the old theoretical arguments transformed into observable reality. The invisible monsters imagined centuries earlier by Michel and Laplace had turned out to exist after all. That realization changed astronomy permanently, because once black holes became accepted as real physical objects, researchers began recognizing their fingerprints everywhere, at galactic centers, inside X-ray binaries, within gravitational wave signals, hidden inside ancient stellar remnants. The universe was not merely stranger than expected, it was stranger than many scientists had actively tried to prevent it from being. One particularly fascinating consequence of black hole physics involves time itself. According to general relativity, strong gravity slows time relative to weaker gravitational regions. Near a black hole, this effect becomes extreme. Imagine two clocks. One remains far from a black hole, the other approaches the event horizon. To the distant observer, the clock near the black hole appears to tick increasingly slowly. Minutes become hours, hours become years. Time stretches under gravity, which means black holes are not merely regions of strong gravity. They are regions where the structure of space-time behaves differently from ordinary human experience, and yet they form naturally from dying stars. That fact alone is astonishing. The universe casually creates objects capable of distorting time itself, not through magic, not through exotic fantasy, just through gravity patiently crushing matter after nuclear fusion ends. In many ways, black holes forced humanity into intellectual humility. They revealed that reality does not care whether humans find certain conclusions intuitive. Nature follows mathematics. Human intuition struggles to keep pace afterward. Even now, black holes remain among the most mysterious objects in science because they sit at the border between two enormously successful theories that still refuse full reconciliation. General relativity describes gravity beautifully on large scales. Quantum mechanics describes microscopic physics with incredible accuracy. But inside black holes, both theories collide. At the center of a classical black hole lies the singularity, a point where density and curvature become effectively infinite according to the equations. Most physicists suspect this signals incomplete understanding rather than literal infinities existing physically. Somewhere inside black holes, quantum gravity likely becomes important. Unfortunately, nature has hidden those regions behind event horizons. Very inconveniently for researchers, it is almost as though the universe enjoys presenting riddles while simultaneously locking the answer inside a vault. Still, despite all the mystery, the existence of black holes themselves is no longer seriously questioned. We have observed stars orbiting invisible massive objects. We have detected gravitational waves from black hole mergers. We have even produced images of black hole shadows using radio telescope networks spanning Earth. Humanity went from doubting black holes entirely to photographing their effects within a single century. That is extraordinary progress for one species, especially one that still occasionally burns microwave popcorn so badly, entire kitchens smell haunted afterward. And perhaps the most remarkable part of all this is how long the idea waited before being accepted. The equations existed. The clues existed. The stars themselves were out there collapsing quietly. But it took centuries before humanity developed the tools, confidence, and imagination necessary to realize the strange, invisible objects predicted by theory were truly woven into the universe around us. Somewhere in the darkness of the Milky Way, long before humans evolved, massive stars were already dying and becoming black holes. Entire cosmic graveyards existed unseen. By the middle of the 20th century, astronomy had entered a slightly chaotic phase. For thousands of years, humans studied the sky mostly through visible light. Telescopes improved steadily, observatories grew larger, and star catalogues became increasingly detailed. Astronomers learned the temperatures of stars, their distances, their chemical compositions, and even how galaxies move through space. It was an extraordinary achievement, and yet, without realizing it, humanity had been observing only a very small fraction of the universe. Visible light is merely one tiny slice of the electromagnetic spectrum. Beyond it exist radio waves, infrared radiation, ultraviolet light, X-rays, gamma rays, and other forms of radiation entirely invisible to human eyes. The cosmos was glowing in all of them constantly. Earth's atmosphere, helpful though it is for breathing and avoiding instant death from radiation exposure, blocks many of these wavelengths from reaching the ground. X-rays in particular are mostly absorbed high in the atmosphere, which meant something remarkable. For almost all of human history, the X-ray universe had been hidden from us completely. The sky people thought they understood was missing some of its most violent and energetic objects. Then rockets arrived. Suddenly scientists could lift detectors above Earth's atmosphere for brief moments. Later, satellites remained in orbit for extended observations. The invisible sky finally opened, and it turned out space was much stranger than expected. Again. X-ray astronomy began revealing objects that seemed almost absurdly energetic. Regions appearing calm in ordinary telescopes blazed violently in X-rays. Exploding stars, neutron stars, superheated gas clouds, and mysterious compact objects lit up the sky in ways no human had ever seen before. Among the brightest of these early discoveries was a source deep inside the constellation Cygnus. Scientists labelled it Cygnus X1. At first glance, the name sounds rather dramatic, but it was actually very practical. Cygnus identified the constellation. X meant the source emitted X-rays. 1 indicated it was the first major X-ray source identified there. Astronomers are often surprisingly straightforward with naming conventions, occasionally disappointingly so. Meanwhile, the object itself was anything but straightforward. The X-ray source was extraordinarily powerful. That alone attracted attention, because X-rays generally require extremely energetic conditions. Ordinary stars like our Sun emit relatively little X-ray radiation compared to their visible light output. To generate intense X-rays, matter usually needs to become unimaginably hot. Millions of degrees hot. Something around Cygnus X1 was producing exactly those kinds of conditions. But what? That question became one of the great astronomical puzzles of the 1960s. Initially, locating X-ray sources precisely was difficult. Early detectors lacked sharp resolution, making it challenging to determine exactly which visible object corresponded to a given X-ray signal. Imagine hearing mysterious noises in a dark room while using blurry glasses. You know something unusual is happening somewhere nearby, but identifying the culprit becomes rather complicated. Astronomers refined their measurements gradually. Better instruments narrowed the source location more accurately until attention focused on a particular visible star known as HDE 26868. At first, it seemed relatively ordinary by stellar standards. Now, ordinary in astronomy can be slightly misleading because HDE 226868 is actually enormous, brilliant, and vastly more powerful than our Sun. It belongs to a class called blue supergiants, some of the hottest and most luminous stars in existence. If our Sun were a cozy neighbourhood fireplace, this star would be an industrial blast furnace having a very bad day. Blue supergiants burn fuel at extraordinary rates. Their immense mass crushes their cores with tremendous pressure, driving nuclear fusion far more aggressively than in smaller stars. As a result, they shine intensely bright, but live relatively short lives. Big stars are strangely wasteful. A small red dwarf star can survive for trillions of years. Massive blue stars burn through their fuel quickly, living only millions of years before collapsing dramatically. Astronomically speaking, they are the cosmic equivalent of someone flooring the accelerator constantly while ignoring every fuel warning light. Still, Even enormous blue supergiants do not normally produce the kind of intense X-rays associated with Cygnus X1. Something else had to be happening nearby. Then astronomers noticed the star behaving oddly. Specifically, it was wobbling. Not visibly to the naked eye, of course. The changes were subtle, detected through spectroscopy, the study of how light shifts depending on motion. When a star moves toward Earth, its light compresses slightly into shorter wavelengths. When it moves away, the light stretches into longer wavelengths. This is called the Doppler effect. It's exactly the same phenomenon responsible for changing ambulance siren pitches as vehicles pass by. Space and traffic share more physics than one might expect. By carefully measuring these spectral shifts over time, astronomers realized HDE 226868 was orbiting something invisible. That was the first major clue. Stars do not wobble randomly for no reason. Orbital motion implies gravity. Gravity implies mass. Something massive enough to tug this enormous star around existed nearby, yet no visible companion could be seen. This immediately narrowed the possibilities. Perhaps the companion was a faint star hidden by brightness differences. Maybe a neutron star. Maybe some unusual stellar remnant. Further measurements complicated matters significantly. The orbital period was about 5.6 days, meaning the two objects orbited each other very closely. Yet despite this tight orbit, only one visible star appeared, and the invisible companion seemed astonishingly massive. That last detail became critical. Astronomers calculated the likely mass based on the visible star's motion. Even conservative estimates suggested the unseen object possessed several times the mass of the Sun. This was deeply uncomfortable. White dwarfs were immediately ruled out because they cannot sustain such masses without collapsing further. Neutron stars, though far denser, also possess upper mass limits. Beyond roughly 2 or 3 solar masses, neutron degeneracy pressure fails. Gravity overwhelms every known force resisting collapse. If the invisible companion truly exceeded those limits, only one known possibility remained: a black hole. At this stage, however, many scientists hesitated to jump towards such a dramatic conclusion. And honestly, that caution was reasonable. Black holes still occupied an uncertain place in physics during the 1960s. General relativity predicted them mathematically, yes, but many astronomers remained uneasy about treating them as genuine physical objects. The equations implied bizarre behavior: trapped light, infinite curvature, warped time. It all sounded rather excessive. Scientists tend to prefer exhausting ordinary explanations before embracing cosmic absurdities. Unfortunately for them, Cygnus X1 kept behaving exactly like a black hole anyway. The X-rays themselves became a major piece of evidence. Researchers realized the radiation could be explained naturally if matter from the blue supergiant star was being pulled toward the invisible companion. Massive stars like HDE 226868 produce strong stellar winds, streams of gas flowing outward into space continuously. If a compact object lurks nearby, gravity can capture some of that material. The gas spirals inward. As it falls, it accelerates enormously. Collisions within the swirling material heat it to millions of degrees, and superheated matter emits X-rays. This process creates something called an accretion disk, one of the most important structures in high-energy astrophysics. Accretion disks are extraordinary environments. Gas orbits at incredible speeds, compressed and heated by friction and gravity, until it becomes plasma hotter than stellar surfaces. The material glows fiercely before finally disappearing inward. In the case of a black hole, once matter crosses the event horizon, it vanishes permanently from observable space, which means the brightest part of the system exists just outside the darkness itself. That contradiction fascinated astronomers immediately. Black holes, despite their name, can indirectly create some of the brightest phenomena in the universe, not because the black hole emits light, because everything around it becomes violently energetic before falling inward. Researchers studying Cygnus X1 noticed the X-ray emission varied rapidly over time. Brightness fluctuations occurred on extremely short timescales. This was another crucial clue. Rapid changes imply a physically small emitting region. Large objects cannot vary brightness instantaneously because light itself takes time to travel across them. The X-ray source appeared compact, very compact. That ruled out many alternative explanations involving large diffuse structures. Everything kept pointing back toward the same disturbing answer. A collapsed object, small, massive, invisible, feeding on nearby stellar material. Exactly what black hole theory predicted. Not everyone agreed immediately, of course. Scientific arguments erupted vigorously throughout the late 1960s and early 1970s. Papers debated the object's mass estimates. Researchers questioned assumptions about stellar properties and orbital geometry. Some scientists actively resisted the black hole interpretation because it felt too extreme. Others became increasingly convinced the evidence was overwhelming. Then came an interesting cultural moment. In 1971, during a friendly scientific bet, physicists Stephen Hawking and Kip Thorne made a wager over whether Cygnus X1 was truly a black hole. Hawking actually bet against it, not necessarily because he fully disbelieved in black holes, but partly because he had spent years studying them theoretically and jokingly wanted insurance in case they turned out wrong observationally. If Cygnus X1 was not a black hole, Hawking would win the bet and at least gain some consolation. If it was a black hole, physics itself would become vastly more exciting. A fairly reasonable trade-off, honestly. Eventually Hawking conceded the bet as evidence strengthened, and strengthen it did. Improved observations refined the companion star's properties. More accurate mass calculations pushed the invisible object further beyond neutron star limits. Radio observations revealed energetic jets associated with accretion processes. The system behaved precisely as black hole models predicted. Astronomers slowly transitioned from cautious skepticism toward broad acceptance. Humanity had likely found the first genuine black hole candidate. That phrase matters slightly. Technically, astronomers still avoid absolute certainty whenever possible. Science rarely uses words like proven forever beyond all imaginable doubt. Instead, researchers build overwhelming evidence until alternative explanations become increasingly implausible. Over time, Cygnus X1 became one of the strongest stellar black hole cases known. And beyond the scientific importance, something about the system captured public imagination immediately. Part of it was proximity. Astronomically speaking, Cygnus X1 is relatively nearby at roughly 6,000 light-years away. That sounds incredibly distant because it is. Yet compared to the size of the Milky Way, it's practically local. Our galaxy spans over 100,000 light-years, so discovering a black hole relatively close to Earth felt strangely personal. Not dangerous, importantly. There is absolutely no threat to Earth from Cygnus X1. 6,000 light-years is an enormous distance. The black hole's gravity affects its local system, not our solar system. Still, humans possess wonderfully dramatic imaginations. The idea that an invisible collapsed star lurks somewhere overhead in the night sky felt unsettling in a very specific way. For centuries, people looked upward assuming darkness mostly meant emptiness. Now, astronomy revealed darkness itself could contain hidden objects more extreme than almost anything previously imagined. And unlike many cosmic discoveries, black holes trigger something deeply instinctive psychologically. Exploding stars are spectacular. Nebulae are beautiful. Galaxies are majestic. Black holes feel hungry. Even though that description is not scientifically precise, it captures the emotional reaction many people experience. Black holes seem active somehow, swallowing matter, trapping light, bending time. They feel less like objects and more like cosmic boundaries where ordinary intuition stops functioning. That sensation became even stranger once scientists understood what falling toward a black hole would actually look like. From the perspective of a distant observer, time near the event horizon slows dramatically because of gravitational time dilation. An astronaut approaching the black hole would appear to move increasingly slowly, fading and reddening gradually. But for the astronaut falling inward, time feels normal. The event horizon itself may not even appear especially dramatic locally. Depending on the black hole's size, you simply continue inward, toward regions where space-time curvature eventually becomes catastrophic. It is one of the strangest consequences of general relativity. Two observers can experience profoundly different realities near strong gravity. And all of this emerged because a star in Cygnus was wobbling oddly. That's one of the most beautiful things about astronomy, really. Tiny clues reveal enormous truths. A subtle spectral shift becomes evidence for warped space-time. Invisible X-rays reveal collapsed stars. Minute orbital motions uncover objects that cannot emit light at all. Humanity learned to detect monsters in darkness using mathematics. Quite an impressive achievement for a species that still misplaces phone chargers with astonishing consistency. As more black hole candidates were discovered later, Cygnus X1 retained special significance because it marked a turning point in scientific thinking. Before it, black holes remained mostly theoretical curiosities. After it, they became astrophysical reality. Astronomers could no longer treat them merely as strange solutions inside Einstein's equations. The universe itself had presented one directly, and once scientists accepted that black holes genuinely existed, an even larger realization followed naturally. If one black hole could form from stellar collapse, then the galaxy should contain many more, perhaps millions, invisible remnants of ancient massive stars scattered silently throughout the Milky Way. Most undetectable unless interacting with nearby matter, which means the night sky above Earth is not simply filled with shining stars and glowing nebulae. It is also filled with unseen gravitational wells drifting quietly through darkness. For most of human history, the universe appeared strangely calm. Yes, there were planets wandering across the sky, occasional comets with dramatic timing, and stars exploding once in a while as supernovae bright enough to alarm entire civilizations. But overall, the night sky looked peaceful, steady, predictable. That impression turned out to be deeply misleading. The problem was not that the universe lacked violence. The problem was that humans were nearly blind to most of it. Our eyes detect only visible light, a very narrow portion of the electromagnetic spectrum. Evolution shaped human vision around sunlight, because that was useful for survival on Earth. Spotting ripe fruit, avoiding cliffs, and noticing whether something with sharp teeth was approaching through tall grass mattered considerably more than detecting gamma rays from distant neutron stars. Natural selection is practical like that. As a result, humanity spent thousands of years studying only a thin slice of cosmic reality. Imagine trying to understand an orchestra while hearing only the violins. Beautiful, certainly, but wildly incomplete. Beyond visible light, the universe hums with radio waves, infrared radiation, ultraviolet light, X-rays, and gamma rays. Entire categories of cosmic phenomena reveal themselves primarily through these invisible forms of radiation, and among the most important of all turned out to be X-rays. Now, X-rays are rather unusual things. Visible light comes from moderately energetic processes, warm stars, glowing objects, ordinary chemistry. X-rays, on the other hand, require extremes. Matter must become incredibly hot or violently accelerated to produce them. Millions of degrees hot. The kinds of temperatures found near exploding stars, neutron stars, and black holes, which means X-rays are often signs of cosmic trouble. If the visible universe resembles a peaceful neighborhood at night, the X-ray universe resembles emergency sirens, industrial fires, collapsing buildings, and occasionally someone setting space-time itself slightly on fire. The strange part is that Earth's atmosphere protects us from most of this radiation automatically. High above the surface, atmospheric gases absorb incoming X-rays before they reach the ground. Excellent news for biology, slightly frustrating news for astronomers. Because of that atmospheric shielding, no ground-based telescope can properly observe cosmic X-rays. For centuries, humanity unknowingly lived beneath a protective curtain, hiding some of the most energetic objects in existence. The invisible sky remained completely inaccessible. Then the space age arrived. Suddenly, scientists could send instruments above the atmosphere using rockets. At first, these missions lasted only minutes, brief upward flights carrying crude detectors into the edge of space before falling back to Earth. Even those short observations changed astronomy forever. In 1962, physicists launched a sounding rocket, equipped with X-ray detectors, led by a team including Riccardo Giacconi, one of the pioneers of X-ray astronomy. Their goal was relatively modest. They hoped to detect X-rays from the moon caused by solar radiation. Instead, they accidentally discovered something astonishing. The strongest X-ray source in the sky after the sun came not from the moon at all, but from deep space. An object later named Scorpius X1. This changed everything. The universe was not quiet in X-rays. It was blazing. And once scientists realized that, a completely new field of astronomy exploded into existence almost overnight. Soon, researchers began launching more rockets, and eventually dedicated satellites to study the high-energy sky. The discoveries became increasingly bizarre. Invisible objects radiated immense energy. Binary star systems behaved violently. Entire galaxies emitted X-rays from their cores. Among the brightest and most mysterious of these sources was Cygnus X1. But before astronomers could understand what it was, they first had to solve a difficult technical problem. How do you observe something invisible? Ordinary telescopes rely on mirrors or lenses reflecting visible light toward detectors. X-rays behave differently. They possess far more energy and tend to pass through ordinary mirrors rather than bouncing cleanly off them. In fact, if you point a normal mirror directly at incoming X-rays, most simply penetrate the material, which is not especially helpful for imaging distant black holes. Scientists eventually discovered a clever workaround. X-rays can reflect if they strike surfaces at extremely shallow angles, almost skimming across them sideways. This led to the development of grazing incidence telescopes, instruments designed specifically for X-ray astronomy. These telescopes looked rather strange compared to ordinary optical telescopes. Instead of simple curved mirrors, they used nested cylindrical mirror structures arranged carefully to guide X-rays toward detectors. Humanity had effectively invented entirely new eyes for observing the universe, and the moment those eyes opened properly, the cosmos became dramatically more unsettling. One fascinating aspect of X-ray astronomy is that it often reveals invisible objects indirectly rather than directly. Black holes themselves emit no light, yet matter falling toward them heats so intensely that the surrounding region blazes brightly in X-rays. This became the key to understanding Cygnus X1. When astronomers first detected the source, they knew only that something extremely energetic existed in the direction of the constellation Cygnus. Pinpointing the exact object required much more precise measurements. Early X-ray detectors were relatively crude by modern standards. They could detect radiation, but struggled to produce sharp images. Imagine trying to identify a candle in a city using blurry binoculars while someone shakes your shoulders constantly. That was roughly the situation. As instruments improved, researchers gradually narrowed the location until attention focused on the massive blue supergiant star HDE 226868. Yet the visible star alone could not explain the intense X-ray emission. Blue supergiants are extraordinarily luminous, yes, but their ordinary radiation peaks mostly in visible and ultraviolet wavelengths. The observed X-rays required something much more energetic. Astronomers realized they might be witnessing accretion. Accretion is one of the most important processes in astrophysics, and also one of the most violent. Gravity pulls matter inward toward a compact object. Instead of falling straight down neatly, the material spirals into an orbiting disk due to angular momentum. As gas circles inward, friction and collisions heat it enormously. Temperatures soar into millions of degrees. At those temperatures, the gas emits X-rays intensely. In essence, black holes create light not by shining themselves, but by causing nearby matter to become catastrophically hot before disappearing. It is an oddly indirect way to announce your existence, rather like being invisible while simultaneously causing surrounding objects to burst into flames. The more scientists studied Cygnus X1, the more perfectly it fit this picture. The visible blue star appeared to be losing material through a stellar wind, streams of gas flowing outward continuously into space. The invisible companion captured some of this material gravitationally. That gas spiraled inward. The gas heated dramatically. X-rays emerged, and because the emitting region was physically tiny, brightness fluctuations occurred rapidly. This last point mattered enormously. Large objects cannot change brightness instantly, because light itself requires time to travel across them. If a source flickers rapidly, it must be compact. The X-ray variations from Cygnus X1 occurred over extremely short timescales, implying the emitting region was small enough to match black hole accretion models beautifully. The invisible object appeared compact, massive, and violently energetic, exactly what theorists expected for a stellar black hole. Still, what made X-ray astronomy revolutionary was not merely the discovery of individual objects. It fundamentally transformed humanity's perception of the universe itself. Before X-ray astronomy, space often seemed cold and static. Afterward, astronomers realized the cosmos is constantly erupting with high-energy processes invisible to ordinary sight. Neutron stars whip magnetic fields around at extraordinary speeds. Supernova remnants blast shockwaves through space. Galaxy clusters contain gas heated to tens of millions of degrees. Supermassive black holes at galactic centers devour matter while launching jets across intergalactic distances. The universe turned out to be profoundly noisy in X-rays. In fact, many of the most extreme objects known are best studied through high-energy radiation, rather than visible light. Black holes in particular often reveal themselves this way, because the event horizon itself remains invisible. You cannot observe the black hole directly. You observe the chaos around it. That realization changed astronomy philosophically, as well as technically. Humans had always associated observation with direct visibility. You see a thing, therefore it exists. Modern astrophysics became far more subtle. Sometimes the most important objects are invisible entirely. You infer them through gravity, through radiation, through orbital motion, through distortions in surrounding matter. Black holes became the ultimate example of this principle. They are defined precisely by their invisibility, and yet they produce some of the brightest environments in the universe indirectly. Another remarkable challenge of X-ray astronomy involves simply operating the instruments themselves. Space is not particularly friendly to delicate electronics. Satellites endure radiation exposure, vacuum conditions, thermal extremes, and orbital mechanics complicated enough to give mathematicians headaches. Early X-ray observatories required extraordinary engineering effort. One major milestone came with the launch of Uhuru in 1970, the first dedicated X-ray astronomy satellite. Named after the Swahili word for freedom, Uhuru catalogued hundreds of X-ray sources across the sky, including improved observations of Cygnus X1. The data strengthened the black hole interpretation significantly. Over time, increasingly advanced observatories followed. Chandra X-ray Observatory, XMM Newton, and others provided far sharper observations of high-energy phenomena throughout the universe. Astronomers could now watch matter orbit near black holes in astonishing detail. They measured temperatures, mapped jets, tracked accretion behavior, studied relativistic effects predicted by Einstein. In many ways, X-ray astronomy became a tool for testing extreme physics directly. Near black holes, gravity becomes so intense that Newtonian intuition fails completely. Time slows, light bends, matter accelerates to relativistic speeds. These effects imprint themselves onto the emitted X-rays. By analysing those signals carefully, astronomers can study the warped space-time surrounding black holes themselves, which is honestly extraordinary. Human beings evolved on a small rocky planet around an average star, yet developed instruments capable of studying distorted space-time thousands of light-years away through invisible radiation. Quite an ambitious species, really. There is also something strangely poetic about the process itself. Black holes cannot be seen because light cannot escape them. So humanity learned to listen instead. Not literally through sound, of course. Space is mostly vacuum, and vacuum carries no sound waves. But X-ray astronomy functions almost like cosmic listening. Scientists detect invisible signals revealing hidden violence in darkness. The universe whispers in wavelengths our eyes never evolved to notice. Technology taught us how to hear them, and once we did, objects like Cygnus X1 suddenly emerged from invisibility. One particularly fascinating aspect of black hole X-ray systems involves efficiency. Nuclear fusion inside stars converts only a small fraction of mass into energy. Accretion near black holes can be vastly more efficient. Matter falling inward releases gravitational energy extraordinarily effectively before crossing the event horizon, which means black hole systems can outshine entire galaxies under the right conditions. A black hole itself remains dark. Yet the process of falling toward one can become among the brightest events in existence. That contradiction still feels slightly unsettling. Darkness producing brilliance, absence creating radiation, invisible gravity illuminating the universe. And in the middle of all this sat Cygnus X1, one of the first objects to force humanity into accepting black holes as physical reality rather than theoretical fantasy. Without X-ray astronomy, the system might have remained hidden indefinitely. The visible companion star alone would never fully reveal the invisible object's nature. It was the high-energy radiation that exposed the truth. The black hole betrayed itself through the destruction of nearby matter. That became one of the great lessons of modern astrophysics. The universe often hides its most important secrets behind forms of light humans cannot naturally perceive. Radio astronomy revealed pulsars, infrared astronomy uncovered hidden star formation, gamma-ray astronomy exposed cosmic explosions, and X-ray astronomy unveiled black holes feeding in darkness. Each new wavelength transformed the universe again. Each revealed reality was larger, stranger, and more energetic than previously imagined. It also changed humanity's relationship with the night sky permanently. The stars above us are no longer merely points of visible light. Behind the darkness exists an invisible cosmos blazing constantly with radiation, collisions, explosions, collapsing stars, and warped space-time. The universe is not sleeping overhead. It is roaring invisibly all the time. We simply lacked the senses to notice until recently. And among the earliest voices humanity learned to hear in that invisible storm was a strange X-ray source hidden inside the Swan, quietly announcing the presence of something with gravity so strong that even light itself could never return. Far out in the constellation Cygnus, two objects circle each other endlessly in the darkness. One of them shines brilliantly, the other cannot be seen at all. Together they form one of the most famous binary systems ever discovered, a partnership so extreme that it helped convince humanity black holes were not merely strange mathematical possibilities, but real physical objects lurking throughout the universe. And like many cosmic relationships, it is both beautiful and deeply unhealthy. The visible member of this system is HDE 226868, a massive blue supergiant star burning with astonishing intensity. The invisible companion beside it is Cygnus X1, the black hole that slowly feeds from the star's outer layers. To understand why this system became so important, it helps to picture just how enormous and violent these stars really are. Our Sun feels immense from Earth because, frankly, it is. Over 1 million Earths could fit inside it. Its core reaches temperatures around 15 million degrees Celsius. Every second, it converts roughly 600 million tons of hydrogen into helium through nuclear fusion. And yet, compared to stars like HD E226868, the Sun is relatively modest. Blue supergiants belong to the upper extremes of stellar mass and luminosity. These stars contain many times the Sun's mass and shine hundreds of thousands of times brighter. Their surfaces blaze at temperatures exceeding 30,000 degrees Celsius, giving them their intense blue-white colour. If our Sun were replaced by a blue supergiant, Earth would not merely become hotter, Earth would cease being a recognisable concept almost immediately. The star's radiation would strip atmospheres, boil oceans, and thoroughly ruin everyone's long-term weekend plans. Massive stars live dramatically because they burn fuel at terrifying rates. Gravity crushes their cores so intensely that nuclear fusion proceeds with enormous efficiency. The energy output becomes staggering. But there is a price. Stars survive through balance. Gravity pulls inward while fusion pressure pushes outward. As long as these forces remain balanced, the star stays stable. In massive stars, however, the fuel disappears quickly because the fusion reactions are so aggressive. The star spends energy recklessly, racing through its life in only a few million years. Smaller stars are patient. Big stars are spectacularly irresponsible. And somewhere around 6,000 light-years away, HD E226868 circles beside the remains of another star that already reached the end of its life long ago. That invisible companion was once massive too, probably even more massive than the blue giant still surviving beside it. At some point in the distant past, the original star exhausted its nuclear fuel completely. Gravity won the battle inside its core. The star collapsed catastrophically, likely exploding outward as a supernova while its central regions compressed inward beyond neutron star limits. The result became a black hole, and somehow, despite all that violence, the binary system survived. That fact alone is extraordinary. Supernova explosions are unimaginably energetic events. Entire stars tear themselves apart. Shockwaves race outward at thousands of kilometers per second. If the explosion becomes too asymmetric or violent, binary companions can easily be flung apart forever. Yet Cygnus X1 and its companion remained gravitationally bound. Now the black hole and blue supergiant orbit each other every 5.6 days. That is astonishingly fast for objects of such enormous mass. For comparison, Earth takes 1 year to orbit the Sun. Mercury, the fastest planet in our solar system, takes about 88 days. These two massive stellar objects complete an orbit in less than a week, which means they are relatively close together astronomically speaking, and that closeness creates the entire drama of the system. The black hole's gravity continuously pulls material away from the blue supergiant, not by sucking like some giant cosmic vacuum cleaner, despite how black holes are often described in films. Gravity simply influences nearby matter strongly enough that gas escaping the star begins spiraling inward. The process starts with stellar wind. Massive stars produce powerful outflows of gas naturally. Radiation pressure from the star's intense luminosity pushes material outward into space constantly. In the case of HDE 226868, this stellar wind is enormous, millions of times stronger than the solar wind from our Sun. The black hole captures part of this outflow gravitationally. Once the gas falls under the black hole's influence, something fascinating happens. The material does not plunge directly inward neatly. Instead, it begins orbiting. This occurs because the gas already possesses angular momentum, sideways motion relative to the black hole. Just like planets orbit stars instead of falling straight inward, The gas circles the black hole while gradually spiralling closer. An accretion disk forms. Accretion disks are among the most violent structures in astrophysics. The orbiting gas becomes compressed, turbulent, and extraordinarily hot. Friction between different layers of material heats the disk to millions of degrees. At those temperatures, atoms break apart completely into plasma, and the plasma emits intense X-rays. That is why Cygnus X1 became visible to X-ray astronomy long before anyone understood what it truly was. The black hole itself emits no light. The material dying around it does. There is something unsettling about that idea. The black hole remains permanently invisible, while the doomed gas around it glows violently in its final moments before crossing the event horizon. Rather like seeing only the spray around a waterfall while the abyss itself remains hidden. And the physics near the black hole grows stranger the closer matter approaches. The inner regions of the accretion disk orbit at enormous fractions of light speed. Magnetic fields twist violently. Temperatures soar. Radiation erupts outward. Near the event horizon, Einstein's relativity becomes essential for describing what happens. Time itself slows relative to distant observers. Light bends around the black hole. Space warps inward, and yet from the perspective of the falling gas, everything proceeds naturally. The material simply follows the geometry of space-time inward. One remarkable aspect of the system is how much energy the black hole extracts from infalling matter. Nuclear fusion inside stars converts less than 1% of mass into usable energy. Accretion onto black holes can be far more efficient. As matter spirals inward, gravitational potential energy transforms into heat and radiation extraordinarily effectively. Before crossing the event horizon, the gas may radiate away a substantial fraction of its mass energy, which means black holes can indirectly become some of the brightest objects in the universe, despite being fundamentally dark. This contradiction still feels almost absurd. The darkest objects produce the brightest environments, and all because gravity is astonishingly efficient at accelerating matter. Astronomers studying Cygnus X1 noticed another intriguing feature as observations improved. The black hole appears to rotate extremely rapidly. This matters because spinning black holes behave differently from non-spinning ones. A rotating black hole drags space-time itself around through an effect called frame dragging. The faster the spin, the more distorted nearby space-time becomes. Imagine stirring honey with a spoon. The honey twists around the rotating object. In a rough sense, spinning black holes do something vaguely similar to space-time itself. Although physicists generally become nervous when black holes are compared to kitchen condiments, still, the principle holds. The black hole's spin affects the inner accretion disk, changing how matter behaves near the event horizon, and influencing how energy escapes from the system. Some black holes even launch enormous jets of high-energy particles outward along their rotational axes. These jets can extend across enormous distances through space. Cygnus X1 produces relativistic jets as well, streams of energetic particles blasting outward at tremendous speeds. Again, all of this activity comes not from the black hole directly, but from the environment surrounding it. Black holes are oddly passive objects in many ways. Gravity does the work. Matter provides the chaos. The black hole simply exists at the center of the violence, warping space-time around itself. Meanwhile, the blue supergiant companion continues losing material gradually over immense stretches of time. This transfer of matter changes both objects slowly. The black hole gains mass. The star loses mass. The orbital dynamics evolve. Binary systems are not static arrangements. They are ongoing gravitational conversations lasting millions of years. And this particular conversation is heading toward a catastrophic ending eventually. Because the blue supergiant itself will not survive forever. Massive stars die dramatically. Once fusion can no longer support the core against gravity, collapse becomes inevitable. Depending on its final mass, the companion star may eventually explode as another supernova and perhaps form a second black hole. If that happens and the system survives, the result could become a binary black hole pair orbiting each other invisibly. Over vast periods, gravitational wave emission would slowly shrink the orbit until eventually the black holes merged in an enormous collision. The universe is patient with these things. What seems permanent on human timescales often becomes temporary on cosmic ones. Yet even now, the system already represents one of the most extreme stellar environments known nearby in our galaxy. The temperatures inside the accretion disk reach millions of degrees, orbital speeds approach relativistic values, gravity warps space-time profoundly, and all of it unfolds beside a star so luminous it would utterly dominate our solar system if placed nearby. There is also something psychologically fascinating about binary systems involving black holes. They reveal how much of astronomy depends on relationships rather than isolated objects. The black hole itself remains invisible. Without the companion star, humanity might never have detected it at all. It is the interaction between the two objects that exposes the hidden physics, the wobbling orbit, the stolen gas, the glowing X-rays, the distorted accretion disk. The entire discovery depended on gravitational influence. In a sense, astronomers learned the black hole existed because of what it did to its companion. That principle appears repeatedly throughout science. Invisible things reveal themselves through effects on visible things. Dark matter alters galactic motion. Exoplanets tug slightly on stars. Black holes distort surrounding matter and radiation. Humanity became remarkably good at detecting things indirectly. Probably because the universe enjoys hiding its most important structures behind inconvenient levels of invisibility. One particularly eerie aspect of Cygnus X1 is that, despite all the violence involved, the system would appear rather ordinary to human eyes from Earth. You would not see swirling X-rays or glowing accretion disks directly. You would simply observe a bright star within the constellation Cygnus. Nothing visually announces the black hole's presence. That feels strangely appropriate somehow. The universe often hides extraordinary realities beneath ordinary appearances. A calm point of light in the night sky can conceal warped space-time and matter heated to millions of degrees. And for centuries humans looked directly toward this system, without realizing what existed there. Only when astronomy learned to detect invisible radiation and subtle stellar motion did the truth emerge. There is also an important reason systems like this matter, scientifically beyond black hole confirmation itself. Binary systems allow astronomers to measure masses much more accurately than isolated objects. Gravity provides the clues. By tracking the companion star's orbit carefully, scientists calculate the invisible object's mass using Newtonian and relativistic dynamics. Those measurements demonstrated convincingly that the unseen companion exceeded neutron star mass limits. Without the binary interaction, proving the existence of stellar black holes would have been vastly more difficult. So in many ways, the blue supergiant became an unwilling witness. Its motion testified to the invisible object beside it. Its stolen gas illuminated the darkness. Its orbit revealed the black hole's mass. The star accidentally helped humanity confirm one of the strangest predictions in modern physics. When astronomers first began suspecting that Cygnus X1 might be a black hole, the reaction within the scientific community was not immediate celebration. It was argument. Long, careful, deeply technical argument, and honestly, that was probably a very good thing. Science advances through skepticism much more often than enthusiasm. Researchers are trained to distrust dramatic conclusions until the evidence becomes overwhelming. Extraordinary claims require extraordinary evidence, as the famous phrase goes. And few claims sounded more extraordinary during the 1960s than this one. We may have found an object where gravity traps light itself. That statement bordered on science fiction at the time. Today, black holes appear everywhere in documentaries, films, books, computer games, and occasionally in advertisements trying much too hard to sell coffee. The term feels familiar now, comfortable even. But during the middle of the 20th century, black holes occupied a very different place intellectually. They were unsettling theoretical predictions hidden inside Einstein's equations. Many physicists accepted the mathematics while quietly hoping reality would avoid producing such absurd objects in practice. This happens surprisingly often in physics. Equations wander somewhere deeply uncomfortable. Scientists pause awkwardly. Then the universe says, yes, that part too. Part of the problem came from general relativity itself. Einstein's theory described gravity not as a force, but as the curvature of space-time caused by mass and energy. The equations were elegant and incredibly successful, explaining planetary orbits, gravitational lensing, and time dilation with astonishing accuracy. But under certain conditions, the equations predicted complete gravitational collapse, matter compressed without limit, escape velocity exceeding light speed, event horizons forming around collapsed stars. Even Einstein himself disliked some of these implications. He suspected nature might somehow prevent true black holes from forming physically, and to be fair, the prediction sounded almost unreasonable. Imagine telling someone in 1920 that stars can collapse into invisible regions where time slows, light cannot escape, and space-time curves inward so strongly that every possible future path leads deeper into darkness. Most people would politely recommend more fresh air. Even many scientists found the idea difficult to accept intuitively because black holes challenge ordinary human understanding so completely. Human intuition evolved for throwing objects, avoiding predators, and navigating landscapes at walking speeds. It did not evolve for interpreting relativistic geometry near collapsed stars. As a result, black holes felt mathematically suspicious to many researchers for decades. Then observations began forcing the issue. By the 1960s, X-ray astronomy revealed objects emitting enormous amounts of high-energy radiation. Binary star systems behaved strangely. Invisible companions appeared too massive to be white dwarfs or neutron stars. And among these systems, Cygnus X1 became the most important test case. The evidence initially looked tantalizing but incomplete. Astronomers knew a massive blue supergiant star, HDE 226868, orbited something invisible every 5.6 days. Spectroscopic measurements showed the visible star wobbling under gravitational influence. That meant an unseen object possessed substantial mass. Meanwhile, the system emitted intense X-rays, strongly suggesting matter was falling toward a compact object and heating violently through accretion. The basic picture fit black hole theory beautifully. But science rarely accepts beautifully as sufficient proof. Researchers immediately began examining alternative explanations. Could the mass estimates be wrong? Could the visible star be less massive than assumed? Could the orbital angle distort calculations? Might the invisible object actually be a neutron star somehow? These questions mattered enormously because the entire conclusion depended on mass. Neutron stars, while incredibly dense, possess upper limits. Beyond roughly 2 or 3 solar masses, neutron degeneracy pressure can no longer resist gravitational collapse. If the invisible companion exceeded that threshold significantly, then a black hole became the only known explanation. But if uncertainties lowered the mass enough, a neutron star remained possible. Astronomers therefore focused intensely on determining accurate system parameters. And that turned out to be difficult. Space rarely hands scientists perfectly convenient experiments. The visible star's properties were uncertain. Blue supergiants are complicated objects with powerful stellar winds and complex atmospheres. Estimating their masses and luminosities involves models with significant uncertainties. Distance measurements also mattered. If the system were farther away or closer than expected, the inferred stellar properties changed. Orbital inclination created another challenge. Imagine observing a spinning coin. Viewed edge-on, the motion appears dramatic. Viewed face-on, the motion becomes harder to interpret. Binary star systems behave similarly. The angle at which astronomers observe the orbit affects measured velocities and derived masses. Small uncertainties in inclination could alter conclusions substantially. This led to years of careful debate. Researchers published competing papers. Mass estimates shifted slightly. Arguments unfolded at conferences and within journals. Some scientists leaned strongly toward the black hole interpretation. Others remained cautious, and underlying everything was a larger philosophical tension about whether black holes themselves truly existed in nature. One fascinating aspect of this period is how emotionally invested some physicists became in the question. Black holes were not merely another category of astronomical object. They represented a profound challenge to human understanding of space, time, matter, and causality. Accepting them meant accepting that the universe genuinely contains regions disconnected from observable reality by event horizons. Places where ordinary intuition breaks down. Places where even time behaves differently. That was a difficult intellectual transition for many researchers. A particularly famous example involved Stephen Hawking and Kip Thorne. In 1974, Hawking made a friendly wager with Thorne over whether Cygnus X1 truly was a black hole. The bet became legendary, partly because Hawking himself had already contributed enormously to black hole physics theoretically. He studied event horizons, singularities, and gravitational collapse extensively. Yet observational certainty still felt elusive enough that he hesitated. Hawking later joked that he made the bet partly as insurance. If black holes turned out not to exist observationally, at least he would win the wager after spending years working on them theoretically. There is something wonderfully human about that. One of the greatest physicists in history quietly hedging against reality itself. The stakes of the bet were amusingly modest compared to the cosmic implications involved. Thorne would receive a subscription to the satirical magazine Private Eye if Hawking lost. Hawking would receive a subscription to Penthouse if he won. Science occasionally becomes stranger than expected in very specific ways. Eventually, Hawking conceded the bet as evidence increasingly favoured the black hole interpretation, and over time that evidence became extraordinarily difficult to dismiss. Improved spectroscopic measurements refined the mass estimates upward. Better stellar modelling strengthened conclusions about the companion star. X-ray variability patterns matched expectations for accretion onto a compact relativistic object. The invisible companion simply appeared too massive and too compact to be anything else known to physics. Meanwhile, theoretical understanding of black holes advanced rapidly during the same period. Physicists like Roger Penrose demonstrated mathematically that gravitational collapse under general relativity naturally produces singularities under realistic conditions. Black holes were not bizarre mathematical accidents anymore. They emerged inevitably from Einstein's equations once massive stars collapsed sufficiently. Theoretical resistance weakened. Observational evidence strengthened. Gradually, the scientific community shifted toward acceptance. Yet even then, astronomers remained careful with language. Cygnus X1 was typically called a black hole candidate, rather than simply a black hole. That distinction reflected scientific caution. Strictly speaking, proving an event horizon directly is extremely difficult because black holes themselves emit no light. Observations rely on indirect evidence, orbital dynamics, radiation signatures, relativistic effects, and the absence of plausible alternatives. Science almost never deals in absolute metaphysical certainty. Instead, it accumulates converging evidence until one explanation becomes overwhelmingly favoured, and eventually the black hole interpretation for Cygnus X1 became overwhelmingly favoured indeed. In hindsight, the arguments may seem almost quaint because black holes are now firmly established astrophysical objects. We have detected gravitational waves from black hole mergers. We have observed stars orbiting supermassive black holes at galactic centres. We have even imaged black hole shadows using global radio telescope networks. But during the 1960s and 1970s, none of that existed yet. Cygnus X1 stood at the frontier between speculation and reality, and frontiers are messy places intellectually. There is another important reason scientists argued so intensely about this system. If Cygnus X1 truly was a black hole, then black holes were probably common throughout the universe. That realization carried enormous consequences. Massive stars are not rare. The Milky Way alone contains hundreds of billions of stars, many far larger than the Sun. If sufficiently massive stars collapse into black holes naturally, then the galaxy should contain countless invisible remnants drifting silently, through space, potentially millions. Suddenly black holes transformed from exotic theoretical curiosities into ordinary products of stellar evolution. The universe became far stranger overnight. It also became much darker, because most stellar black holes remain invisible unless interacting with nearby matter strongly enough to betray themselves through radiation, which means the galaxy could be filled with unseen gravitational wells entirely undetectable by ordinary observation. That idea unsettled people profoundly, not because black holes pose practical danger to Earth. Importantly, space is unimaginably vast. The nearest known stellar black hole systems are far away, and gravity weakens rapidly with distance. The discomfort was philosophical. Humans had spent centuries imagining the night sky primarily as a landscape of visible stars. Now astronomy revealed that invisible collapsed stars might outnumber visible stellar remnants in some regions. Darkness itself contained hidden structure. One especially fascinating aspect of the scientific debate involved the role of indirect evidence. Black holes cannot be observed directly because no light escapes them. This forced astronomers into a fundamentally different style of reasoning. You infer black holes through consequences, orbital motion, accretion disks, X-ray radiation, relativistic effects, gravitational influence. In a sense, black holes taught astronomy how to study absences, and that became increasingly important later in astrophysics. Dark matter, exoplanets, gravitational waves, and many modern discoveries rely heavily on indirect detection methods. Often the universe reveals itself not through what can be seen directly, but through subtle effects on surrounding systems. Cygnus X1 became one of the earliest great examples of this principle. The black hole itself remained invisible, yet everything around it betrayed its presence. The companion star wobbled gravitationally, the accretion disk blazed in X-rays, matter accelerated relativistically near the event horizon, jets emerged from the system. The invisible object announced itself through physics, and gradually the objections faded, not because scientists became less skeptical, because the evidence became too strong. That distinction matters enormously. Good science does not begin by believing extraordinary claims enthusiastically. It tests them relentlessly. It searches for errors, alternatives, uncertainties, loopholes. Only when the claim survives those attacks does acceptance emerge. In many ways, the long argument over Cygnus X1 strengthened black hole science tremendously. Researchers were forced to refine observations, improve models, and confront difficult questions carefully. The skepticism made the eventual conclusion far more convincing, and once the community largely accepted stellar black holes as real, astrophysics entered a new era. Black hole candidates multiplied. Supermassive black holes appeared at galactic centers. Quasars gained clearer explanations. Relativistic astrophysics expanded rapidly. Eventually, gravitational wave astronomy confirmed black hole mergers directly. What once sounded almost absurd became foundational to modern cosmology. Still, there remained something charming about those early years of uncertainty. Scientists staring at strange X-ray signals, arguing over orbital inclinations and mass estimates, quietly debating whether the universe truly permits regions where light itself cannot escape, And somewhere above them all, inside the constellation Cygnus, the black hole simply continued orbiting its companion star, unconcerned entirely with whether humanity believed in it yet or not. Suppose, for just a moment, that you could travel to Cygnus X1, not merely observe it from Earth through telescopes and X-ray detectors, but actually approach the system itself. Imagine drifting through the darkness toward the black hole and its blazing blue companion star, watching the strange geometry of space-time unfold around you. It would be one of the most extraordinary and deeply unpleasant journeys imaginable. Now, before we continue, there is some mildly reassuring news. No human being will ever accidentally fall into Cygnus X1. It sits roughly 6,000 light-years away, which is an almost absurd distance by everyday standards. Even travelling at the speed of our fastest spacecraft, the trip would take millions of years. So if you are worrying about slipping into a nearby black hole sometime next Tuesday afternoon, you may relax. Still, black holes provoke curiosity precisely because they represent environments so extreme that ordinary intuition stops functioning. People naturally ask the question eventually, what would actually happen if you fell into one? The answer depends partly on the size of the black hole involved. Smaller black holes behave differently from enormous supermassive ones. Cygnus X1 belongs to the category called a stellar mass black hole, formed from the collapse of a massive star. Current estimates place its mass at roughly 20 times that of our Sun. That may not sound enormous compared to supermassive black holes containing millions or billions of solar masses, but remember something crucial. All that mass is compressed into an extraordinarily tiny region compared to a star, and gravity near compact objects changes rapidly with distance, very rapidly. If Earth somehow became a black hole while keeping the same mass, its event horizon would measure only about the size of a marble. The mass remains unchanged. The density becomes absurd. This means stellar black holes possess incredibly steep gravitational gradients nearby. Gravity at your feet can become dramatically stronger than gravity at your head over relatively short distances. And unfortunately for hypothetical astronauts, the human body is not designed for that sort of experience. Scientists have a wonderfully cheerful term for what happens next: spaghettification, which sounds almost whimsical until you realize it refers to being stretched into a long, thin strand by tidal gravity. Physics occasionally names horrifying things with alarming casualness. To understand why this happens, imagine falling feet first toward a stellar black hole. Your feet are slightly closer to the black hole than your head, so gravity pulls harder on them. Normally, gravitational differences across the human body are tiny. Earth's gravity affects your feet only negligibly more strongly than your head. Near a stellar black hole, however, the difference becomes catastrophic. Your lower body accelerates inward faster than your upper body. At the same time, tidal forces compress you sideways. You stretch vertically and squeeze horizontally. Eventually, atoms themselves cannot hold together against the tidal stresses, which is scientifically speaking rather bad for long-term survival. The exact details depend on how close you approach before the tidal forces become lethal. Around a stellar mass black hole like Cygnus X1, the dangerous region extends relatively far from the event horizon because the black hole is compact. Ironically, supermassive black holes can be gentler initially. Their event horizons lie much farther from the central singularity, so tidal forces at the horizon itself may be surprisingly mild. You could theoretically cross the event horizon of a sufficiently large supermassive black hole without immediately noticing anything unusual locally. Stellar black holes are less polite. Approaching Cygnus X1 would likely become fatal well before crossing the event horizon itself. And honestly, the accretion disk alone would already present a fairly serious obstacle. Remember, Cygnus X1 is actively feeding from its companion star. Gas spiraling inward forms a superheated accretion disk emitting intense X-rays and other radiation. Temperatures there reach millions of degrees. Any spacecraft approaching recklessly would encounter radiation levels capable of thoroughly destroying electronics and biological tissue long before reaching the event horizon. So the journey would involve several increasingly unfortunate stages. First comes lethal radiation exposure, then tidal distortion, then complete structural disassembly, and only after all that would whatever remains continue inward toward the black hole itself. Not exactly an ideal vacation itinerary. Still, the truly fascinating part of black hole physics is not merely the destruction, it is how different observers perceive the fall. This is where Einstein's relativity begins behaving in deeply counterintuitive ways. Imagine two observers, one falls toward the black holes, the other remains far away watching safely from a distance. Their experiences diverge dramatically. From the perspective of the falling astronaut, time feels perfectly normal. Your heartbeat continues steadily. Your thoughts proceed normally. Your wristwatch ticks as usual. Relativity does not feel strange locally. You continue falling inward and naturally through curved space-time. But to the distant observer watching you approach the event horizon, something extraordinary happens. You appear to slow down. More specifically, clocks near the black hole run increasingly slowly relative to distant clocks because of gravitational time dilation. Light escaping from your spacecraft also becomes redshifted, stretched into longer wavelengths as gravity drains energy from it. So from far away your image appears dimmer, redder and slower over time. You never seem to cross the event horizon completely. Instead, you appear to freeze near it gradually while fading from view. This is one of the strangest consequences of relativity. From your perspective, you cross the event horizon in finite time. From the distant observer's perspective, you asymptotically approach it forever. Both descriptions are correct within their own frames of reference. Reality near black holes becomes deeply observer-dependent. There is something profoundly unsettling about that. The universe permits situations where different observers genuinely experience time differently because space-time itself is curved. And this is not merely theoretical speculation. Gravitational time dilation has been measured experimentally many times near Earth using atomic clocks. Black holes simply magnify the effect enormously. Another bizarre feature involves the appearance of the outside universe during your fall. As you approach the event horizon, light from distant space becomes distorted and blue-shifted. Depending on your trajectory, the external universe may appear increasingly compressed into strange patterns around you. Meanwhile, time outside may seem accelerated. Distant clocks appear to run faster relative to your own. If you somehow survived long enough near the event horizon, you could theoretically witness external events unfold more rapidly. The farther inward you travel, the stranger space-time geometry becomes. Eventually, ordinary ideas about direction stop functioning intuitively. Outside a black hole, space offers many possible future paths. You can move north, south, upward, downward, or remain stationary. Inside the event horizon, however, all future directed paths lead inward. This is an astonishing statement physically. The singularity becomes not merely a location in space, but effectively part of your future in the same unavoidable sense that tomorrow normally lies ahead in time. Within the event horizon, moving away from the singularity becomes as impossible as moving backward through time. Space-time geometry itself forces inward motion. Human language struggles badly at this point because our brains did not evolve to visualize curved, four-dimensional space-time under extreme gravity. Words like inside, toward, and future begin overlapping strangely. And then there is the singularity itself. According to classical general relativity, matter falling inward eventually reaches a point of effectively infinite density and curvature. Most physicists suspect this description signals incomplete understanding rather than literal infinities existing physically. Quantum gravity likely becomes important near such extreme conditions. Unfortunately, current physics lacks a complete quantum theory of gravity, which means black hole interiors remain among the greatest unsolved problems in science. The event horizon hides the answer from direct observation entirely. Nature has effectively locked the deepest physics inside a cosmic vault. Rather rude of it, honestly. One especially fascinating question concerns information. What happens to the information describing matter that falls into a black hole? This issue became one of the most famous debates in theoretical physics. Quantum mechanics suggests information cannot truly disappear from the universe, yet black holes appear to erase accessible information behind the event horizon. Then Stephen Hawking discovered something even stranger in the 1970s. Black holes are not completely black after all. Through quantum effects near the event horizon, they emit faint thermal radiation now called Hawking radiation. Over immense timescales, black holes may gradually evaporate. This creates the famous black hole information paradox. If a black hole eventually evaporates entirely, what happens to all the information about everything that fell inside? Modern physics still lacks full consensus on the answer, which means black holes remain not merely astrophysical objects, but fundamental puzzles about the nature of reality itself. And all of this strange physics exists inside Cygnus X-1 tonight, while it quietly orbits beside its companion star. There is something remarkable about that thought. The night sky above Earth contains real objects where time distorts dramatically, where space-time geometry traps light, and where modern physics reaches the edge of its understanding. Not in some distant fantasy universe, in our galaxy, right now. Of course, if humans ever approach such environments practically, engineering challenges would become overwhelming long before the event horizon itself. Radiation shielding, tidal forces, orbital mechanics, energy requirements, and relativistic effects would all pose enormous obstacles. Black holes are not merely dangerous because of gravity. They are dangerous because the surrounding environments become violently energetic. Accretion disks produce intense radiation fields. Magnetic fields twist unpredictably. Jets launch relativistic particles outward. The region near an actively feeding black hole resembles an industrial disaster happening inside a physics experiment conducted by the universe itself. Not ideal for tourism, still, scientists study these environments passionately, because black holes function as natural laboratories for extreme physics impossible to reproduce on Earth. Near black holes, gravity becomes strong enough that relativity dominates visibly. Matter accelerates to enormous speeds. Magnetic fields reach extraordinary strengths. Time dilation becomes significant. These systems allow researchers to test physical theories under conditions unavailable anywhere else. In a sense, black holes are the universe performing experiments for us. Dangerous experiments, spectacular experiments. Experiments we observe very carefully from extremely far away. One subtle point often misunderstood involves crossing the event horizon itself. Popular culture sometimes portrays it as a dramatic barrier or glowing surface. In reality, the event horizon is not a physical wall. It is a boundary in space-time. If you crossed it inside a sufficiently large black hole, without strong tidal forces nearby, you might not notice anything special locally at the exact moment of crossing. No alarm sounds, no cosmic sign flashes. You simply continue inward while losing all possible future escape paths. That may actually be more unsettling than a dramatic barrier. The universe often hides its strangest transitions behind ordinary appearances, and perhaps that captures something essential about Cygnus X-1 itself. From Earth, the system appears as an ordinary point of light in the constellation Cygnus. Nothing visible suggests warped space-time or trapped light. Nothing announces the event horizon. Yet somewhere inside that distant darkness exists a region where gravity reshapes reality so profoundly that all future paths lead inward forever. And the remarkable thing is that humanity figured this out not by visiting the black hole, but by studying starlight, X-rays, orbital motion, and mathematics from thousands of light years away. Quite an achievement for a species still occasionally surprised by automatic doors. If black holes themselves are invisible, then why do some of them become among the brightest objects in the universe? That question puzzled astronomers for years because it seems completely contradictory at first glance. A black hole, by definition, traps light. Nothing escapes once it crosses the event horizon. So how can something designed by physics to be perfectly dark end up creating enormous amounts of radiation visible across galaxies? The answer lies not inside the black hole itself, but in the chaos surrounding it. And around Cygnus X1, that chaos becomes extraordinarily violent. The key structure is called the accretion disk, a swirling disk of superheated gas spiraling inward toward the black hole. It is one of the most energetic environments known in astrophysics, and one of the clearest demonstrations that gravity, under the right conditions, can become astonishingly efficient at producing energy. In fact, accretion onto black holes can release more energy than nuclear fusion itself. That is a remarkable statement when you stop to think about it. Fusion powers stars. Fusion drives the sun. Fusion converts mass into energy through the very reactions governing stellar life. And yet matter falling toward a black hole can outperform it. Not because the black hole generates energy magically, but because gravity accelerates in falling matter so intensely that enormous amounts of gravitational potential energy become heat and radiation before the material disappears beyond the event horizon. To understand how this works, imagine water spiraling down a drain. The closer the water gets to the center, the faster it moves. Friction and turbulence develop naturally within the flow. Now replace the sink drain with a collapsed star containing 20 times the sun's mass compressed into a tiny region of warped space-time. Also increase the temperatures to millions of degrees and perhaps remove any expectation of survival. That begins approaching the physics of an accretion disk. Around Cygnus X1, the process starts with the blue supergiant companion star HDE 226868. The star continuously loses gas through a powerful stellar wind driven outward by intense radiation pressure. Some of that gas drifts close enough to the black hole for gravity to capture it. But the gas does not fall straight inward neatly. Almost nothing in space does. The material already possesses sideways motion relative to the black hole, so instead of plunging directly inward, it begins orbiting. Gravity pulls the gas closer while angular momentum keeps it circling. A rotating disk forms naturally. This same basic principle appears throughout the universe. Planets form from rotating disks around young stars. Galaxies rotate. Saturn's rings orbit in flattened structures. Angular momentum is one of nature's favourite ways of organising matter. Around black holes, however, the process becomes much more extreme. The gas inside the accretion disk moves at extraordinary speeds. Inner regions orbit faster than outer regions, creating friction and turbulence within the disk. Magnetic fields twist through the plasma chaotically. All that motion generates heat, immense heat. The temperatures near the inner disk around Cygnus X1 become so high that atoms cannot remain intact. Electrons separate from nuclei completely, creating plasma, an ionized state of matter sometimes called the fourth state beyond solids, liquids, and gases. The plasma glows intensely in X-rays. This is why astronomers first discovered the system through X-ray observations. The black hole itself remains invisible, but the dying material around it becomes one of the brightest X-ray sources in the sky. There is something almost cruelly ironic about it. The darkest objects in existence reveal themselves through overwhelming brightness nearby. In a way, the accretion disk acts like the black hole's fingerprint. Different compact objects create different radiation patterns depending on their mass, rotation, and environment. By studying the emitted X-rays carefully, astronomers can infer details about the invisible black hole itself. This includes one particularly fascinating property: spin. Black holes can rotate, and not just gently. Many spin extraordinarily fast. The black hole in Cygnus X1 appears to rotate near the maximum speed allowed by general relativity. That spin profoundly affects the surrounding space-time and the behavior of the accretion disk. A rotating black hole drags space-time around itself through frame dragging. The effect becomes stronger closer to the event horizon. Imagine stirring thick syrup with a spoon. Nearby syrup twists around the rotating object. Spinning black holes do something conceptually similar to space-time itself. Again, physicists may sigh slightly at the kitchen analogy, but the general idea works. The faster the spin, the closer stable orbits can exist near the black hole. Matter in the accretion disk can spiral deeper inward before plunging across the event horizon. That matters enormously because deeper orbits release more gravitational energy, which means rapidly spinning black holes can generate even brighter accretion disks. The region near the inner disk becomes one of the most extreme environments in nature. Matter circles at significant fractions of light speed. Temperatures soar into millions of degrees. Magnetic turbulence twists plasma violently, and all this occurs around something fundamentally invisible. One especially strange aspect of accretion disks involves efficiency. When matter falls onto ordinary stars or planets, much of the gravitational energy dissipates relatively modestly. Black holes are different because matter can descend extraordinarily deep into the gravitational well before disappearing. The resulting energy release becomes enormous. Depending on the black hole's spin, accretion can convert roughly 10% or more of infalling mass energy into radiation. Fusion inside stars converts less than 1%. That means black hole accretion is among the most efficient energy generation mechanisms known. A surprisingly productive outcome for an object famous primarily for swallowing things. The emitted radiation from accretion disks also varies over time, and those fluctuations reveal important clues. Around Cygnus X1, astronomers observe rapid X-ray variability, changes occurring over fractions of a second sometimes. This tells scientists the emitting region must be physically small, because large objects cannot vary brightness instantaneously. Light itself requires time to travel across space. A giant object changes slowly. A compact object can flicker rapidly. These fluctuations became one of the major pieces of evidence supporting the black hole interpretation early in the system study. The X-rays behaved exactly as expected for hot plasma orbiting near a compact relativistic object. And then there are the jets. Some black hole systems produce enormous beams of high-energy particles launched outward perpendicular to the accretion disk. Cygnus X1 emits such jets as well. The exact mechanism remains complex and not fully understood, but magnetic fields likely play a crucial role. Twisted magnetic structures around the spinning black hole and accretion disk channel enormous energies into narrow relativistic outflows. Particles accelerate to near light speed. Radiation erupts across vast distances. Again, the black hole itself does not emit the jets directly in the ordinary sense. The surrounding accretion environment generates them through extreme electromagnetic and relativistic processes. It is important to remember just how violent these conditions really are. The accretion disk is not a calm, swirling cloud. It is catastrophic. Matter collides constantly at enormous speeds. Radiation floods outward intensely. Magnetic turbulence churns through superheated plasma. If you somehow approach the inner disk around Cygnus X1, the radiation alone would destroy you long before gravity became the main concern. And yet from Earth, the system appears peaceful. A distant point of light in the constellation Cygnus. That contrast remains one of astronomy's most fascinating themes. The universe often hides extraordinary violence behind ordinary appearances. A quiet star overhead may conceal an invisible black hole feeding from superheated plasma nearby. And for centuries, humanity looked directly toward this region of space without suspecting what unfolded there. Only when X-ray astronomy emerged did the hidden violence become visible. One remarkable consequence of accretion physics is that black holes become easier to detect while feeding actively. Isolated black holes drifting alone through space remain almost impossible to observe directly because they emit virtually no radiation, but add nearby matter, and suddenly the black hole becomes dramatically obvious through the behaviour of the accretion disk. This means astronomers often discover black holes not by seeing them, but by seeing what they do to surrounding material. The accretion disk acts almost like a warning flare around the event horizon. Another fascinating feature involves the inner edge of the disk itself. Material cannot orbit stably arbitrarily close to the black hole. Eventually the space-time geometry becomes too extreme. Inside a certain radius called the innermost stable circular orbit, matter plunges rapidly inward. The location of this boundary depends on the black hole's spin. By studying emitted X-rays carefully, astronomers can estimate where the inner disk terminates and thus infer the black hole's rotation rate. Incredible amounts of information hide inside those X-ray signals. Humanity learned to decode them gradually through decades of observation and theoretical work. There is also something psychologically strange about accretion disks, because they transform gravity into visible destruction. Gravity itself is usually gentle on human scales. It keeps planets orbiting, objects falling, oceans flowing. Near black holes, gravity becomes terrifyingly energetic. Matter accelerated by gravity alone can reach relativistic speeds. Temperatures exceed stellar interiors. Radiation floods outward across space. And yet the underlying force remains the same gravity keeping your feet on Earth tonight, just operating under conditions far beyond ordinary human experience. One subtle point often misunderstood involves the event horizon itself. The glowing accretion disk is not the black hole. The event horizon lies inside the bright swirling material. Beyond that boundary, no light escapes. So when people see artistic images of glowing black holes surrounded by fiery disks, the actual black hole is the dark central region. The brightness belongs to doomed matter still outside the horizon. Matter making one final brilliant announcement before vanishing permanently from observable space. That image affected scientists profoundly when black hole systems first became accepted observationally. The accretion disk transformed black holes from abstract mathematical solutions into physically observable environments. You could not see the black hole directly, but you could watch the universe falling into one, and perhaps that is what made systems like Cygnus X1 so compelling. The black hole remained invisible, yes, yet its presence reshaped everything around it. Gas glowed in X-rays, matter spiraled inward, jets blasted through space, time distorted near the horizon, space-time curved violently. The darkness itself became visible indirectly through its effects. There is something almost philosophical about that. Some of the most important things in the universe reveal themselves only through influence rather than direct observation. Gravity itself cannot be seen. Dark matter remains invisible. Black holes trap light completely, and yet all of them reshape reality around them so strongly that their existence becomes undeniable. In the end, the accretion disk around Cygnus X1 taught humanity an extraordinary lesson. Darkness is not always empty. Sometimes the brightest phenomena in existence form around things that cannot be seen at all. There is a boundary around a black hole where physics becomes deeply strange, not explosive strange, not dramatic in the way films often portray it, strange in a quieter, more unsettling sense. A place where ordinary ideas about movement, time and direction stop behaving the way human intuition expects. That boundary is called the event horizon, and around Cygnus X1 it marks the point beyond which nothing can ever return. Not matter, not signals, not light, not even information in the ordinary sense. For many people, the event horizon sounds like some kind of physical surface, perhaps a glowing shell surrounding the black hole like the edge of a storm cloud. But it is not a material object. You cannot touch it directly, because it is not made of atoms or plasma or gas. The event horizon is a boundary in space-time itself, a geometric limit, a point of no return created purely by gravity. And one of the strangest things about it is this: if you somehow crossed the event horizon of a large enough black hole, you might not notice the exact moment it happened. No alarm would sound, no cosmic gate would appear, no invisible wall would suddenly stop you. Locally, physics would seem normal. You would simply continue falling inward. That detail alone disturbed physicists profoundly when they first understood it fully. Human beings naturally expect important boundaries to feel dramatic. Crossing a border, entering a storm, falling from a cliff, all produce clear sensory changes. The event horizon does not necessarily behave that way. Reality outside and inside follows the same local physical laws. What changes is the structure of space-time itself. To understand why, it helps to think carefully about escape velocity again. Around ordinary objects like Earth, escape remains possible if you move fast enough. Rockets leave Earth because they exceed escape velocity. Spacecraft escape the Sun if accelerated sufficiently. Near a black hole, however, escape velocity eventually exceeds the speed of light. And since nothing can travel faster than light, escape becomes impossible. But relativity describes this more subtly than Newtonian physics. The event horizon is not merely a place where gravity becomes too strong, in the ordinary sense. It is a region where all possible future-directed paths through space-time lead inward. That sentence sounds abstract initially, but it carries enormous meaning. Outside a black hole, you may choose many possible directions through space. Forward, backward, left, right, away from the black hole. Inside the event horizon, every future path points deeper inward. Not because some force drags you unwillingly, because space-time geometry itself has changed. And this is where the famous statement comes from that space and time switch places inside a black hole. Now, that phrase is somewhat simplified, but it points toward a genuinely bizarre feature of general relativity. Outside the event horizon, moving through time is unavoidable, while moving through space involves choice. You can decide whether to walk north or south, but you cannot decide whether tomorrow arrives. Time moves forward inevitably. Inside the event horizon, inward motion toward the singularity becomes similarly unavoidable. The singularity lies in your future in much the same way tomorrow normally does. Trying to avoid the singularity becomes as impossible as trying to stop moving forward through time. This is extraordinarily difficult for the human brain to visualize because our intuition evolved entirely within weak gravitational environments. We do not experience warped space-time naturally, yet mathematically, this behavior emerges inevitably from Einstein's equations. The event horizon reshapes causality itself, and around Cygnus SS1, that geometry exists right now, hidden inside the darkness surrounded by the glowing accretion disk. One fascinating consequence involves communication. Suppose an astronaut somehow approached the event horizon while sending signals outward continuously. To distant observers, those signals would become increasingly redshifted as gravity stretched their wavelengths. The transmissions would slow and fade gradually. Eventually the signals would become too weak and stretched to detect. From the outside perspective, the astronaut appears frozen near the horizon, dimming forever. But from the astronaut's own perspective, nothing special happens locally at the horizon itself. They continue inward normally. This apparent contradiction is not a mistake. Relativity genuinely allows different observers to experience time differently depending on gravity and motion. Near black holes, those differences become extreme. There is something deeply unsettling about that realization, because it undermines the idea of a universal shared present moment. Time near a black hole does not behave the same way as time far away. Reality becomes observer-dependent in a very literal physical sense, and yet all of this has been experimentally supported indirectly through gravitational time dilation measurements near Earth, neutron stars and other relativistic environments. Black holes merely push the effect to its ultimate limit. Now, if the event horizon itself already sounds strange, the region deeper inside becomes even more mysterious. Because beyond the horizon lies the singularity, or at least that is what classical general relativity predicts. The singularity is often described as a point of infinite density, where space-time curvature becomes infinite as well. Matter collapsing inward compresses without limit. But most physicists strongly suspect that infinities in equations usually signal incomplete understanding, rather than literal physical infinities existing in nature. This is where general relativity and quantum mechanics begin colliding with each other. General relativity describes gravity beautifully on large scales. Quantum mechanics describes microscopic reality with astonishing accuracy. Inside black holes, however, both become simultaneously important, and modern physics still lacks a complete theory unifying them fully, which means nobody actually knows with certainty what truly exists at the centre of a black hole. That is remarkable. Humanity discovered black holes observationally. We understand event horizons reasonably well. We measure black hole masses and spins. We observe accretion disks and gravitational waves. And yet the ultimate fate of matter inside the horizon remains one of the greatest unsolved problems in science. Nature has hidden the answer behind a boundary from which no information escapes. A rather effective security system, honestly. One particularly strange implication involves the nature of time itself. Outside a black hole, humans experience time as flowing steadily forward. Seconds pass, clocks tick, causes precede effects. Inside extreme relativistic geometries, however, ordinary distinctions between space and time begin blending mathematically. The black hole interior becomes a region where our familiar mental categories stop applying cleanly. This does not mean time literally transforms into space in some simple visual sense. Rather, the geometry governing possible motion changes fundamentally, and all this unfolds naturally from Einstein's field equations. No science fiction required, just gravity operating under sufficiently extreme conditions. Another extraordinary feature involves the appearance of the external universe during infall. If you approach the event horizon of Cygnus X1 somehow safely, light from outside space would become increasingly distorted around you. Depending on your motion and location, the visible universe could appear warped into strange arcs and compressed patterns due to gravitational lensing. The black hole bends light dramatically. Stars behind it would appear displaced and distorted. The sky itself would no longer behave normally. And because of relativistic time effects, the external universe might appear to evolve faster relative to your local clock. Distant stars would age more rapidly from your perspective. Clocks outside the gravitational well would run faster. The farther inward you travelled, the more disconnected your experience would become from distant reality. Eventually escape becomes impossible not because you lack strength or propulsion, but because space-time itself no longer contains outward future paths. That distinction is crucial. Black holes are not cosmic vacuum cleaners sucking objects inward from huge distances aggressively. If our sun magically became a black hole with identical mass, Earth would continue orbiting normally because gravity at Earth's distance would remain unchanged. The event horizon matters only nearby. Black holes are dangerous because close space-time geometry becomes extreme, very extreme. This also means falling into a black hole differs dramatically depending on the black hole's size. For stellar black holes like Cygnus X1, tidal forces become lethal before or near the event horizon. The gravitational difference across the human body becomes catastrophic. Feet accelerate inward much faster than the head. You stretch vertically and compress sideways. Spaghettification occurs. Again, physics occasionally names horrifying things with suspicious cheerfulness. Supermassive black holes behave differently because their event horizons are much larger. Tidal forces at the horizon itself may remain relatively mild initially. A sufficiently large supermassive black hole could theoretically allow an astronaut to cross the horizon before strong tidal destruction begins. Not that this improves the long-term survival prospects very much. the singularity still waits deeper inside eventually. One of the most important discoveries related to black holes came from Stephen Hawking in the 1970s. Using quantum field theory near event horizons, Hawking discovered black holes are not completely black. They emit faint thermal radiation now called Hawking radiation. This happens because quantum mechanics allows particle-antiparticle fluctuations near the horizon. Under certain conditions, one particle escapes while the other falls inward. To distant observers, the black hole appears to radiate energy slowly. Over immense timescales, black holes may eventually evaporate entirely. This was revolutionary because it connected black hole physics to thermodynamics and quantum mechanics simultaneously. Suddenly, event horizons possessed entropy and temperature. Black holes became thermodynamic objects, and that created one of the deepest puzzles in modern physics, the black hole information paradox. If information cannot be destroyed in quantum mechanics, what happens to the information carried by matter falling into a black hole? Does it vanish forever? Is it encoded somehow on the horizon? Does Hawking radiation preserve it subtly? Modern theoretical physics still debates these questions intensely, which means the event horizon is not merely an astrophysical boundary. It is one of the central battlegrounds in humanity's attempt to understand reality fundamentally. There is something almost poetic about that, though not in the dreamy abstract sense. The most important unsolved problems in physics may hide inside objects that cannot be observed directly, because light itself cannot escape them. The universe built mysteries into darkness physically. And yet, despite all this exotic physics, black holes remain natural consequences of stellar evolution. Massive stars live, fuse elements, collapse, and sometimes leave behind regions where space-time curves inward beyond escape. The process is not magical. It is gravity following Einstein's equations relentlessly. That may actually be the strangest part. The laws of physics governing apples falling from trees also govern event horizons around collapsed stars. The same gravity keeping planets in orbit can eventually reshape time itself under extreme enough conditions. The event horizon of Cygnus X1. Invisible, untouchable. A boundary where ordinary human ideas about direction and time stop working properly. A region where all future paths curve inward forever, and humanity discovered it not by travelling there, but by decoding starlight and gravity carefully enough to realise the impossible had been sitting quietly in our galaxy all along. When Cygnus X1 first emerged as a serious black hole candidate, it did something larger than merely expand astronomy. It strengthened one of the most extraordinary scientific theories ever created, because hidden behind every discussion of accretion disks, event horizons, and warped space-time cites the work of Albert Einstein. And in a strange way, black holes became one of the ultimate confirmations that Einstein's understanding of gravity was correct, which is slightly ironic. Einstein himself was never entirely comfortable with black holes. That happens sometimes in science. Researchers create theories more powerful and unsettling than they initially expect. The mathematics wanders into territory the creator finds deeply strange. Then the universe quietly says, yes, that part too. To understand why black holes mattered so much for relativity, it helps to remember what gravity meant before Einstein arrived. Under Isaac Newton, gravity was understood as a force acting between masses. The sun pulled Earth. Earth pulled the moon. Objects attracted each other across space invisibly. Newton's theory worked astonishingly well. It predicted planetary orbits accurately enough to guide navigation, engineering, and astronomy for centuries. But there were tiny cracks. One famous example involved the orbit of Mercury. Mercury moves around the Sun in an ellipse, but the ellipse itself slowly rotates over time, a phenomenon called perihelion precession. Most of that motion could be explained through gravitational interactions with other planets, but not all of it. A small discrepancy remained stubbornly unresolved. Astronomers searched for explanations endlessly. Some proposed hidden planets. Others modified gravitational assumptions. Nothing worked completely. Then Einstein arrived. In 1915 he published General Relativity, one of the most revolutionary theories in scientific history. Instead of treating gravity as a force, Einstein described it as geometry, mass curves space-time. Objects follow those, curves naturally. Gravity becomes the shape of reality itself. This sounds abstract initially, but the consequences were extraordinary. Einstein's equations explained Mercury's strange orbital motion perfectly, without inventing hidden planets or arbitrary corrections. That alone was remarkable. Then came another dramatic test. Einstein predicted gravity should bend light. According to general relativity, starlight passing near the Sun would follow curved space-time slightly, shifting the apparent positions of stars during a solar eclipse. In 1919, astronomers led by Arthur Eddington measured the effect successfully during an eclipse expedition. Einstein became internationally famous almost overnight. Newspapers announced that Newtonian gravity had been overthrown, which was slightly exaggerated because Newtonian gravity still works extremely well under ordinary conditions. But Einstein's theory clearly described reality more completely. And then relativity kept winning, again and again. Gravitational redshift, time dilation, gravitational lensing. Eventually even GPS satellites required relativistic corrections to function accurately because time flows differently in weaker gravitational fields and moving frames. Your phone navigation system works partly because Einstein was correct about time itself. Quite an impressive contribution for someone whose hair appeared permanently engaged in its own separate physical experiment. Still, black holes represented something even more extreme. Einstein's equations predicted that if enough mass collapsed inward, space-time could curve so strongly that an event horizon would form. Light itself would become trapped. Time and space would behave strangely near the boundary, and according to classical relativity, collapse would continue toward a singularity. These predictions disturbed many physicists profoundly because they sounded almost absurd. Even Einstein doubted nature would truly allow such objects to form physically. But the equations refused to cooperate with human discomfort, and eventually Cygnus X1 forced astronomers to confront the issue observationally. The system behaved exactly as relativistic black hole theory predicted. An invisible compact object orbited beside a massive blue supergiant. Matter spiraled inward through an accretion disk. X-rays erupted from superheated plasma. The inferred mass exceeded neutron star limits. Everything fit. It was one of the clearest moments where Einstein's equations stopped being abstract mathematics and became visible astrophysical reality. That mattered enormously because black holes are fundamentally relativistic objects. Newtonian gravity alone cannot describe them properly. Under Newtonian physics, gravity acts across space as a force. Escape velocity can exceed light speed mathematically, yes, but Newtonian theory lacks event horizons, warped space-time, or relativistic causality. Black holes, as modern physics understands them, emerge specifically from general relativity. So every confirmed black hole effectively became another major victory for Einstein's framework. And Cygnus X1 helped lead that transition. One especially important aspect involved time dilation near the black hole. General relativity predicts clocks run differently depending on gravity. Stronger gravitational fields slow time relative to weaker ones. Near a black hole, this effect becomes extreme. Matter orbiting close to Cygnus X1 experiences distorted spacetime geometry. Light escaping the inner accretion disk becomes redshifted gravitationally. Orbital motion approaches relativistic speeds. Astronomers studying X-ray emissions observed behaviors matching relativistic predictions beautifully. The black hole effectively became a laboratory for testing gravity, under extraordinary conditions impossible to reproduce on Earth. And the deeper researchers looked, the better relativity performed. That pattern repeated throughout modern astrophysics. Neutron stars confirmed relativistic effects. Gravitational lensing bent light around galaxies. Binary pulsars lost energy through gravitational waves exactly as Einstein predicted. Then, in 2015, almost exactly a century after general relativity was published, the LIGO scientific collaboration detected gravitational waves directly for the first time. The source: two black holes merging, ripples in space-time itself crossing the universe. Einstein won again, and remarkably, black holes helped provide some of the strongest confirmations, because black holes exist precisely where gravity becomes dominant enough for relativity to matter enormously. Ordinary environments often hide relativistic effects because gravity remains relatively weak. Black holes magnify them dramatically. One particularly fascinating consequence involves the innermost stable orbits around black holes. In Newtonian gravity, stable circular orbits can exist arbitrarily close to a mass if velocity adjusts properly. General relativity changes that. Near black holes, space-time curvature becomes so strong that stable orbits cease below a certain radius. Matter inside this boundary spirals inward rapidly. Astronomers studying accretion disks around systems like Cygnus X1 observe evidence consistent with these relativistic orbit predictions. Again and again, Einstein's geometry matches reality. And perhaps the strangest part is how unintuitive the theory remains despite all this evidence. General relativity is not merely difficult mathematically, it is difficult psychologically. Human brains evolved under weak gravity at low speeds. Everyday life does not prepare us for warped space-time, gravitational time dilation, or event horizons. The theory feels strange because reality itself becomes strange under extreme conditions. There is something almost humbling about that. The universe is under no obligation to align with human intuition. Black holes demonstrate this beautifully. Imagine explaining the event horizon to someone unfamiliar with relativity. A region where future-directed paths all lead inward. A place where distant clocks appear to speed up relative to local time. An invisible boundary formed entirely by geometry. It sounds fictional. And yet systems like Cygnus X1 exist quietly in our galaxy, behaving exactly this way. Another important reason black holes strengthened relativity involved spin. General relativity predicts rotating masses drag space-time around them through frame dragging. Around spinning black holes, the effect becomes enormous. Cygnus X1 appears to rotate extremely rapidly, close to the maximum rate allowed by relativity. This spin influences the accretion disk, jet formation, and inner orbital structure. Observations increasingly supported these relativistic models. Once again, Einstein's equations described reality under extreme gravity astonishingly well. Of course, black holes also revealed limitations in current physics. General relativity predicts singularities, regions where density and curvature become effectively infinite. Most physicists suspect quantum effects eventually modify this picture somehow. The problem is that general relativity and quantum mechanics remain fundamentally difficult to unify completely. Black holes sit precisely at the border between them. That means black holes simultaneously confirm Einstein's theory and expose its incompleteness. General relativity works beautifully outside the event horizon. Inside, especially near singularities, something deeper likely awaits. This is part of why black holes fascinate physicists so intensely. They are not merely exotic astronomical objects, they are clues, natural laboratories pointing toward future physics. And systems like Cygnus X1 became crucial because they transformed black holes from theoretical curiosities into observable reality. Once black holes became observationally accepted, relativity itself gained an entirely new arena of experimental testing. Then came even more astonishing confirmations. In 2019, the Event Horizon Telescope collaboration released humanity's first image of a black hole shadow around the supermassive black hole in the galaxy, Messier 87. The image matched relativistic predictions strikingly well, a glowing accretion structure surrounding a dark central shadow caused by the event horizon's gravitational effects. Again, Einstein won. By this point, relativity had survived more than a century of increasingly precise tests across scales ranging from satellites near Earth to black hole mergers billions of light years away. That is one of the greatest success stories in scientific history, and yet what makes it even more remarkable is that Einstein developed the theory mostly through thought experiments and mathematical reasoning long before observational technology could test many predictions directly. He imagined riding beams of light. He reconsidered simultaneity and acceleration. He reconstructed gravity conceptually from first principles. Then the universe spent the next century confirming his ideas repeatedly. Quite an extraordinary outcome. Still, there is a subtle irony at the centre of all this. Einstein personally resisted some implications of his own equations, particularly black holes and certain cosmological conclusions. He famously introduced the cosmological constant partly to keep the universe static because he disliked the idea of cosmic expansion. Then astronomers discovered the universe really is expanding. Another reluctant victory. Black holes followed a similar pattern. Einstein's equations predicted them naturally. Einstein doubted nature would realize them physically. Then objects like Cygnus X1 appeared. Reality once again chose the stranger option. Perhaps that is one of the deepest lessons in modern physics. Human intuition is not a reliable guide to cosmic truth. Mathematics often reaches reality first, and black holes became among the clearest examples of this phenomenon. Long before telescopes detected X-rays from accretion disks, Einstein's equations already contained the possibility hidden inside them. The universe simply waited patiently for humanity to catch up. And tonight, somewhere within the swan-shaped constellation stretching across the Milky Way, Cygnus X1 continues curving space-time exactly as general relativity predicts. And every orbit, every X-ray fluctuation, every warped path of light continues quietly confirming that Einstein's strange vision of gravity was not merely mathematics. It was reality all along. One of the most unsettling things about Cygnus X1 is not merely that it exists, it is where it exists. Not at the far edge of the observable universe, not hidden in some impossibly distant galaxy barely visible through giant telescopes, but here, inside the Milky Way, relatively nearby in cosmic terms. Now, the phrase nearby becomes slightly dangerous in astronomy, because space has a habit of completely destroying ordinary human intuitions about distance. If someone says a grocery store is nearby, they usually mean a short walk or perhaps a 5-minute drive. If astronomers say something is nearby, they may mean it is only several thousand light years away instead of several million. The universe operates on scales so enormous that language itself begins struggling to keep perspective properly. Still, by galactic standards, Cygnus X1 genuinely is fairly close to Earth. Current measurements place it roughly 6,000 light-years away. That sounds unimaginably distant because it is unimaginably distant. A light-year is the distance light travels in 1 year, about 9.46 trillion kilometers. Light moves at nearly 300,000 kilometers per second, fast enough to circle Earth more than 7 times in a single second. And even at that speed, reaching Cygnus X1 takes approximately 6,000 years. The light-entering telescopes today left the system long before the rise of modern civilization on Earth. When those photons began travelling toward us, humans had not yet built the Roman Empire. Most of Europe lacked written history entirely. Iron tools were relatively new in many regions, and meanwhile, the black hole continued feeding quietly beside its blue supergiant companion star. Space is wonderfully rude about reminding humanity how recent we are. Still, within the scale of the Milky Way, 6,000 light-years is not especially far. Our galaxy spans over 100,000 light-years across. The solar system sits roughly halfway between the galactic centre and outer edge. Many objects studied in astronomy lie millions or billions of light years away. Compared to those distances, Cygnus X1 is practically local. That realization affected scientists and the public profoundly when the black hole interpretation became widely accepted, because it meant one of the strangest objects predicted by modern physics was not merely some exotic curiosity in a distant, unreachable region of the cosmos, it was part of our galactic neighborhood. The Milky Way itself contains black holes, possibly millions of them, and one of the first confirmed examples sits relatively nearby overhead tonight. There is something psychologically different about nearby cosmic objects. Distant galaxies feel abstract. Black holes billions of light years away seem detached from everyday human existence. But objects inside our own galaxy feel personal somehow. They belong to the same stellar system we do, the same rotating disk of stars, the same gravitational family. And perhaps even stranger is the fact that humans look toward the constellation Cygnus for thousands of years without suspecting a black hole lurk there at all. To the naked eye, nothing looks threatening. The constellation itself is beautiful. Ancient sky watchers saw the shape of a swan flying along the Milky Way, wings stretched across the heavens. On dark, clear nights, it remains one of the most recognizable patterns in the northern sky, and somewhere within that calm arrangement of starlight sits a collapsed star, where space-time curves inward so strongly that even light cannot escape. The universe hides extraordinary things quietly sometimes. One reason the distance to Cygnus X1 matters scientifically is because distance influences almost every other measurement astronomers make. Brightness depends on distance. Mass estimates depend partly on luminosity. Orbital calculations improve with accurate positional data. Early uncertainty about the system's distance complicated black hole mass estimates significantly. Astronomers spent decades refining those measurements carefully. Eventually, techniques involving parallax and radio interferometry improved accuracy dramatically. By observing tiny positional shifts as Earth orbited the Sun, researchers determined more precise distances. This strengthened the black hole interpretation further because better distance measurements refined the properties of the companion star and orbital system. And once those numbers settled more clearly, the invisible object's mass became increasingly difficult to explain as anything except a black hole. The system itself also belongs to a larger stellar environment inside the Milky Way. Cygnus X1 likely formed within a region rich in massive stars because giant stars rarely form in isolation. Massive stars live short lives, astronomically speaking. They burn through fuel rapidly and die within only millions of years. That means they cannot drift very far from their birthplaces before collapsing. The black hole itself therefore represents the remnant of a massive ancient star that once shone brilliantly in our galaxy, before collapsing catastrophically. Long before humans existed, this stellar death already occurred. That idea is fascinating in its own quiet way. The black hole in Cygnus X1 formed millions of years ago. Entire evolutionary eras passed on Earth while the system continued orbiting silently through the galaxy. Dinosaurs vanished. Mammals evolved. Humans appeared. Civilizations rose and fell, all while the black hole remained there unnoticed. There is also a slightly unsettling implication hiding inside all this. If astronomers found one nearby stellar black hole relatively easily because it interacts with a companion star, how many isolated black holes drift invisibly through the Milky Way undetected? Quite possibly many. Most black holes emit little or no radiation, unless feeding actively from surrounding matter. A solitary black hole travelling through interstellar space may remain almost impossible to observe directly. It would not glow. It would not announce itself. Only gravity would reveal its presence subtly. Modern estimates suggest our galaxy may contain millions of stellar mass black holes formed from ancient collapsed stars. Most are effectively invisible. The Milky Way may therefore contain far more black holes than humans once imagined, and yet there is no practical reason for fear. Space is staggeringly empty. Even though black holes may be common on galactic scales, the distances between stars remain enormous. The nearest known black holes lie very far away from Earth, and gravity weakens rapidly with distance. A black hole does not roam through space swallowing everything nearby like a cosmic vacuum cleaner. That image belongs mostly to science fiction. If our Sun magically became a black hole while retaining identical mass, Earth would continue orbiting almost exactly as before. We would freeze without sunlight eventually, which would admittedly create certain inconveniences, but gravitationally the orbit remains stable. Black holes become dangerous only at close range. Very close range. Still, humans naturally react emotionally to nearby black holes because they represent something fundamentally alien in ordinary experience. Planets make sense intuitively. Stars make sense. Even exploding stars remain understandable conceptually as giant cosmic eruptions. Black holes feel different. They are regions where geometry itself behaves strangely, places where time slows, where future paths curve inward inevitably, where light cannot escape, and one of them exists only a few thousand light-years away. Another fascinating point involves how we define close, cosmically at all. Consider this. The nearest star system beyond the Sun, Alpha Centauri, lies about 4.3 light-years away. Humanity has never sent a spacecraft even remotely close to reaching another star. Our fastest probes would still require tens of thousands of years to travel that distance. Compared to everyday life, even nearby stars are astonishingly remote. So when astronomers casually describe Cygnus X1 as relatively close, they are speaking entirely within galactic scales. And galactic scales are enormous beyond normal comprehension. One subtle but important detail about the system is its location within the plane of the Milky Way. The night sky towards Cygnus contains dense stellar fields because we are looking through the galactic disk itself. The Milky Way band visible across dark skies represents the combined light of countless distant stars concentrated along the galaxy's plane. Hidden among those stars are stellar nurseries, neutron stars, gas clouds, supernova remnants, and black holes. The galaxy is far busier and more crowded than the naked eye suggests, and modern astronomy revealed that many of its most important structures remain invisible in ordinary light. X-ray astronomy uncovered feeding black holes. Radio astronomy revealed pulsars. Infrared observations exposed hidden star-forming regions buried inside dust clouds. Humanity slowly learned that visible light alone tells only a small fraction of the cosmic story. Another intriguing aspect of Cygnus X1 involves its motion through the galaxy. Measurements suggest the black hole likely formed without an extremely violent supernova kick. That surprised astronomers because many stellar remnants receive large velocity boosts during asymmetric explosions. Instead, the system appears comparatively calm dynamically. This implies the original star may have collapsed more quietly than expected, perhaps directly into a black hole with a weaker explosion. Again, the universe complicated human assumptions. Researchers expected dramatic behavior. Reality may have chosen subtlety instead. There is also something philosophically strange about receiving ancient light from black holes. Every observation of Cygnus X1 shows the system as it existed thousands of years ago. Astronomy always looks backward in time because light requires time to travel. The farther away an object lies, the older the observed information becomes. When astronomers observe distant galaxies billions of light-years away, they literally see ancient cosmic history. Even nearby galactic objects involve delayed information, which means the black hole system overhead tonight may already differ slightly from what telescopes currently observe. The companion star may have shifted subtly. The accretion disk may have changed brightness states. Matter continues spiraling inward, while Earth receives old photons carrying delayed news. Space and time intertwine constantly in astronomy. One especially remarkable feature of modern astrophysics is how precisely humans can study objects so distant. Scientists measure masses, spins, orbital periods, radiation spectra, and relativistic effects from thousands of light years away using careful analysis of light and physics. Humanity never visited Cygnus X1, we likely never will, yet we know an extraordinary amount about it. That achievement becomes even more impressive when remembering that black holes themselves emit no light directly. Astronomers inferred the invisible object through gravitational influence, X-ray radiation from the accretion disk, orbital motion, and relativistic behaviour. The black hole revealed itself indirectly, and perhaps that captures something important about science itself. Reality often hides behind appearances. Human beings learn to uncover invisible structures not by direct experience, but through evidence, mathematics, and patient observation. The black hole in Cygnus X1 became one of the clearest examples of that process, a dark object inside the Milky Way, relatively nearby, invisible to the eye, and yet now understood well enough that we can discuss its mass, spin, accretion physics, and warped space-time from a small rocky planet thousands of light-years away, which is honestly an extraordinary thing for any species to accomplish, especially one still occasionally forgetting passwords despite inventing relativistic astrophysics. Whenever people hear the words black hole and nearby in the same sentence, a very understandable question usually follows. Should we be worried? And to answer immediately before anyone starts nervously checking the night sky tonight, the answer is no. Cygnus X1 poses absolutely no danger to Earth. None. Not tomorrow. Not in a million years. Not unless the laws of physics suddenly develop a deeply unreasonable sense of humour. Still, the fear itself makes sense because black holes occupy a strange place in human imagination. They sound dangerous instinctively. A region where gravity traps light feels less like an ordinary astronomical object and more like some cosmic disaster waiting to happen. Popular culture certainly encouraged that impression. Films often portray black holes as giant vacuum cleaners rampaging through space, swallowing planets, stars, spacecraft, and occasionally entire plots with questionable scientific accuracy. Reality is much calmer. Stranger, certainly, but calmer. To understand why Cygnus X1 cannot threaten Earth, the first thing to remember is distance. The system lies roughly 6,000 light-years away. That distance is enormous beyond ordinary human comprehension. Light itself, moving at nearly 300,000 kilometers per second, requires 6 millennia to travel from the black hole to Earth. Everything we observe from the system today actually happened thousands of years ago. Any physical influence travelling at or below light speed would require equally immense travel times. Gravity itself follows this rule under relativity. Changes in gravitational fields propagate at light speed, not instantaneously, which means even if something dramatic happened near Cygnus X1 right now, Earth would not know for thousands of years. But even beyond the time delay, gravity weakens dramatically with distance. This is one of the most important things people misunderstand about black holes. Black holes are not cosmic predators actively sucking objects inward from huge distances. Gravity depends on mass and distance, not whether an object happens to be a black hole. If the Sun somehow became a black hole while keeping identical mass, Earth's orbit would remain almost unchanged gravitationally. We would continue orbiting normally. The solar system would not suddenly collapse inward. There would simply be no sunlight anymore, which would admittedly cause a number of practical inconveniences rather quickly. The key idea is this. At large distances, a black hole's gravity behaves just like the gravity of any other object with the same mass. What makes black holes extraordinary is not that they possess magical long-range suction. It is that they compress large amounts of mass into extremely tiny regions, creating extreme gravity only nearby, very nearby. The event horizon around Cygnus X1 is tiny compared to interstellar distances, Outside the immediate vicinity, the black hole behaves gravitationally much like any compact massive object, so Earth remains completely unaffected. Another reason people sometimes worry involves the accretion disk and X-ray emissions. After all, Cygnus X1 produces intense high-energy radiation as matter spirals inward. Could those X-rays harm Earth somehow? Again, no. By the time the radiation travels 6,000 light-years through space, it becomes extremely diluted. Earth receives only tiny detectable amounts requiring specialized instruments to observe. The atmosphere blocks most incoming cosmic X-rays anyway. That shielding is one reason life on Earth survives at all. The universe is full of high-energy phenomena constantly. Supernovae explode. Neutron stars emit radiation. Black holes feed from accretion disks. Fortunately, space is incredibly large. Distance protects us. One interesting hypothetical concern scientists do study involves nearby supernovae or gamma-ray bursts. Extremely energetic explosions occurring sufficiently close to Earth could potentially affect the atmosphere or biosphere. But sufficiently close means vastly closer than Cygnus X1, and importantly, the black hole itself is not likely to produce such a catastrophic event aimed at Earth anyway. The companion star HDE 226868 eventually will die because massive stars always do. It may explode as a supernova sometime in the distant future, but even then, the distance remains so enormous that Earth would not face serious danger. The explosion might become visible in the sky historically speaking, perhaps even bright enough for future civilizations to notice dramatically, but it would not sterilize the planet or destroy the solar system. Again, the cosmos is violent. It is also wonderfully spacious. Still, humans remain fascinated by the idea of threatening black holes, partly because they feel fundamentally alien compared to ordinary objects. Planets and stars behave intuitively enough. We understand burning spheres of gas conceptually. Black holes challenge deeper assumptions. They involve warped space-time, event horizons, and trapped light. That naturally triggers imagination, and imagination tends to escalate quickly, especially when combined with words like singularity, which admittedly does sound rather ominous. Another common fear involves wandering black holes drifting invisibly through space. Could an unseen black hole someday pass dangerously close to the solar system? In principle, isolated black holes probably do wander throughout the Milky Way because they form from ancient collapsed stars. But again, space is staggeringly empty. The average distances between stars are enormous. Even if millions of stellar black holes exist in our galaxy, collisions or dangerous close encounters remain extraordinarily unlikely. Astronomy sometimes sounds terrifying until you remember how much emptiness separates everything. To appreciate that emptiness properly, consider scale carefully. If the Sun were the size of a small coin, Earth would orbit several meters away. The nearest star beyond the Sun would still lie hundreds of kilometers distant at that scale. Galaxies are mostly vacuum. Solar systems are mostly vacuum. Atoms themselves are mostly empty space. The universe contains huge amounts of nothing between the interesting parts. That emptiness protects us constantly. One subtle but fascinating point involves gravitational influence from the center of the Milky Way itself. At our galaxy's center lies Sagittarius A star, a supermassive black hole containing millions of solar masses. And yet Earth remains perfectly safe because the distance is immense, roughly 26,000 light-years. The solar system orbits the galaxy normally just as planets orbit stars. Again, black holes are not uniquely dangerous at large distances. They obey gravity like everything else. In many ways, the fear surrounding black holes reflects how deeply humans dislike invisible threats. A volcano feels understandable because you can see it. A storm announces itself clearly. Black holes remain hidden. You infer them indirectly through gravitational effects and radiation from nearby matter. That invisibility creates psychological unease. The event horizon especially unsettles people because it represents a one-way boundary in nature. Cross inward and escape becomes impossible. Human beings naturally react strongly to irreversible situations, and black holes embody irreversibility physically. Still, there is a major difference between being conceptually frightening and being practically dangerous. Tigers are dangerous nearby. Lightning is dangerous nearby. Black holes are dangerous only if you get extraordinarily close. Earth is not close. Not remotely close. One amusing consequence of this misunderstanding is that people occasionally imagine black holes growing uncontrollably by swallowing everything around them indefinitely. But accretion depends entirely on available matter. Cygnus X1 feeds from its companion star because the star sits nearby and loses gas through stellar winds. Without surrounding matter, black holes do very little visibly. An isolated black hole drifting through interstellar space remains mostly quiet and invisible. Gravity alone cannot magically pull distant stars inward unless orbital conditions allow it. The black hole's influence remains local, very local, compared to galactic scales. There is also another important point rarely discussed in science fiction. Black holes are not immortal cosmic monsters growing forever necessarily. Through quantum effects discovered by Stephen Hawking, black holes emit Hawking radiation very slowly. Over unimaginable timescales, they may eventually evaporate completely. For stellar black holes, this process takes vastly longer than the current age of the universe. Still, the fact remains remarkable. Even black holes are temporary eventually. The universe slowly erodes almost everything given enough time. Another fascinating reason Cygnus X1 interests scientists despite posing no threat is that it serves as a natural laboratory for extreme physics. Near the black hole, gravity becomes strong enough for relativistic effects to dominate visibly. Matter accelerates to enormous speeds, magnetic fields twist violently, time dilation becomes significant. Researchers can study Einstein's relativity under conditions impossible to recreate on Earth. In this sense, black holes become scientifically valuable precisely because they exist safely far away. Humanity gets the benefit of observing extreme environments without needing to survive inside them personally. Quite a fortunate arrangement, really. There is also something comforting about how ordinary the larger universe remains, despite containing black holes. The Milky Way has likely hosted black holes for billions of years. Stars formed, stars died. Black holes emerged naturally, and throughout all that time, planetary systems continued orbiting peacefully across the galaxy. Life evolved on Earth, while stellar remnants silently drifted through space elsewhere. The cosmos does not resemble a battlefield filled with aggressive black holes hunting matter dramatically. It resembles a vast gravitational ecosystem governed by distance, motion, and time. Most objects never come remotely close to each other, and perhaps that is one of the deeper lessons astronomy teaches repeatedly. The universe feels frightening partly because human intuition struggles with scale. Black holes sound terrifying until you realize how tiny they are compared to interstellar distances. Supernovae sound catastrophic until you calculate how far away they occur. Galaxies collide, yet individual stars almost never hit each other because space is so empty. Cosmic violence and cosmic emptiness coexist constantly. One final subtle point deserves mentioning. Although Cygnus X1 poses no danger physically, black holes do threaten something else slightly more vulnerable: human certainty. Before black holes became accepted, many scientists doubted nature would truly permit such strange objects to exist. Event horizons, singularities, warped time, trapped light, all seemed too bizarre. Then the universe quietly produced them anyway. That may be the real discomfort black holes create. They remind humanity that reality is stranger than intuition. The galaxy contains regions where ordinary concepts of time and space fail. Invisible collapsed stars drift silently through darkness. and one of the first confirmed examples sits relatively nearby inside the Milky Way, while Earth continues orbiting safely under a calm sky. When humanity first confirmed that Cygnus X1 was almost certainly a black hole, the discovery changed far more than one corner of astronomy. It changed the way humans understood the universe itself. Before objects like Cygnus X1, black holes occupied an uncertain space between mathematics and imagination. They existed inside equations, yes, but many scientists still treated them almost like theoretical oddities. Interesting, uncomfortable, perhaps not entirely real. Then astronomy looked carefully toward the constellation Cygnus and found a system behaving exactly the way Einstein's equations predicted. An invisible object, too massive to be a neutron star, feeding from a companion star, emitting powerful X-rays through an accretion disk, warping nearby space-time through extreme gravity. At that moment, black holes stopped being merely speculative. The universe itself confirmed them. And once that happened, humanity's picture of reality expanded dramatically. One of the first lessons Cygnus X1 taught us was surprisingly simple. The cosmos is under no obligation to remain intuitive. That may sound obvious now, but historically humans repeatedly assumed nature would avoid excessively strange behaviour. When equations predicted bizarre outcomes, scientists often suspected some hidden correction would restore common sense eventually. Yet again and again, the universe refused. Relativity predicted time dilation. Reality agreed. Quantum mechanics predicted uncertainty and wave-particle duality. Reality agreed again. Black holes predicted trapped light and warped space-time. Reality apparently approved of those too. There is something deeply humbling about that pattern. Human intuition evolved on the surface of a relatively calm planet, under weak gravity at slow speeds. We experience only a tiny fraction of physical possibility directly. The universe itself is vastly stranger than the environment that shaped our instincts, and black holes became one of the clearest demonstrations of this truth. Another profound lesson involved invisibility. For most of history, humans assumed observation required seeing things directly. Stars emit light, planets reflect sunlight, galaxies glow. Black holes change that completely. The defining feature of a black hole is precisely that it cannot be observed directly in the ordinary sense. Light cannot escape the event horizon, and yet humanity still discovered them. That required a major shift in scientific thinking. Astronomers learned to study invisible objects through consequences instead of appearances. The companion star's wobble revealed hidden gravity. The accretion disk exposed superheated plasma. X-rays betrayed matter spiraling inward. Relativity predicted the geometry. The black hole itself remained unseen while everything around it testified to its existence. This became one of the most important methodological lessons in modern astrophysics. Reality often reveals itself indirectly. Dark matter works this way too. Exoplanets were first detected through stellar motion and brightness changes. Gravitational waves distort space-time subtly, rather than appearing visually. Modern astronomy increasingly studies effects rather than objects themselves, and in many ways Cygnus X1 helped humanity become comfortable with that approach. The discovery also transformed our understanding of stars. Before relativistic astrophysics matured, stars often seemed relatively permanent in the human imagination. Modern astronomy revealed something much more dramatic. Stars are temporary. They live, they evolve, they die, and massive stars die violently. The black hole in Cygnus X1 formed because an enormous ancient star exhausted its nuclear fuel millions of years ago. Gravity overwhelmed every force resisting collapse. The stellar core imploded into a region where space-time itself became trapped. That realization fundamentally altered humanity's view of the night sky. The stars overhead are not eternal lights. They are stages in cosmic evolution. Some become white dwarfs, some become neutron stars, some collapse into black holes. The universe recycles matter continuously through stellar birth and death, and occasionally the result becomes something so extreme that light itself cannot escape. Another astonishing lesson involved energy. Before black holes were studied seriously, nuclear fusion seemed almost unimaginably powerful already. The sun converts hundreds of millions of tons of mass into energy every second. Then, accretion physics around black holes revealed something startling. Gravity can outperform fusion. Matter spiraling toward a black hole releases enormous amounts of energy through heating and relativistic effects before crossing the event horizon. Accretion disks became among the brightest structures in existence. This reshaped astronomy profoundly because it explained some of the most energetic phenomena in the cosmos: quasars, active galactic nuclei, relativistic jets. Suddenly, researchers understood that black holes power many of the universe's brightest engines indirectly. The darkest objects create the brightest environments. Again, the universe preferred the stranger option. One particularly important insight involved scale. At first, stellar black holes like Cygnus X1 seemed exotic enough already. Then astronomers realized supermassive black holes exist at the centers of galaxies, including our own Milky Way. The implications became enormous. Black holes were not rare accidents. They appeared woven throughout cosmic structure itself: galaxy evolution, star formation, relativistic jets, and high-energy astrophysics all connected back to black holes in some way. The discovery of one stellar black hole candidate helped open the door toward an entirely new understanding of galactic architecture. And perhaps most importantly, Cygnus X1 strengthened humanity's confidence in general relativity under extreme conditions. Einstein's theory predicted black holes long before observational evidence existed. Many scientists doubted such bizarre objects would physically form. Then nature quietly built them anyway. This reinforced a remarkable pattern in physics history. Mathematics often reaches truth before intuition catches up. Relativity described warped space-time accurately. Black holes emerged naturally from the equations. The universe validated the theory experimentally through systems like Cygnus X1. That success gave physicists confidence to push relativity even further, eventually leading toward gravitational wave astronomy, event horizon imaging, and modern cosmology. One subtle but important lesson involved humility. Black holes revealed that the universe contains regions where current physics becomes incomplete. General relativity predicts singularities. Quantum mechanics resists information destruction. Event horizons create paradoxes involving entropy and causality. Modern science still does not fully understand what happens inside black holes. That is extraordinary. Humanity confirmed their existence observationally. We measure their masses and spins. We study accretion disks and relativistic jets. Yet the deepest internal physics remains mysterious. Black holes became reminders that scientific success does not eliminate mystery. Sometimes understanding expands mystery instead. The more researchers learned about black holes, the more profound the unanswered questions became. What happens to information inside event horizons? How does quantum gravity behave? Do singularities truly exist physically? Can space-time itself emerge from deeper structures? Black holes sit directly at the boundary between what humans know and what reality may still conceal. And perhaps that is part of why they fascinate people so intensely. They are not merely astronomical objects, they are intellectual frontiers. There is also something psychologically revealing about humanity's reaction to black holes. People fear them instinctively despite the fact that nearby black holes pose essentially no practical threat to Earth. The fear comes partly from invisibility and irreversibility. Black holes represent boundaries where escape becomes impossible, where information disappears from view, where ordinary assumptions fail. In many ways, they symbolize the limits of human control and understanding. And yet humans pursued understanding anyway. That may be the most remarkable lesson of all. A species evolved for survival on an African savanna eventually became capable of discovering invisible collapsed stars thousands of light years away using mathematics and X-ray detectors. That achievement is astonishing when considered carefully, especially because black holes themselves are so deeply counterintuitive. Human brains did not evolve to comprehend curved space-time naturally. We cannot visualize four-dimensional geometry intuitively. Event horizons violate ordinary experience. Time dilation feels unreal emotionally even though experiments confirm it repeatedly. And yet through mathematics, observation, and persistence, humanity learned to study these objects successfully. The discovery of Cygnus as one therefore became not only a story about astrophysics, but also a story about human intelligence itself. Our species learned to infer invisible realities from subtle evidence. That ability changed civilization entirely. The same reasoning process underlies modern science broadly. Atoms cannot be seen directly with human eyes. Neither can magnetic fields, viruses, space-time curvature, or quantum wave functions. Humans learn to detect hidden structures through effects. Black holes simply represent one of the most dramatic examples. Another fascinating consequence of black hole research involved technology. X-ray astronomy required entirely new instruments and observational methods. Space telescopes became essential because Earth's atmosphere blocks X-rays naturally. To study black holes, humanity had to leave the ground. In a sense, black holes helped drive the development of modern space-based astronomy itself, and those technologies later expanded understanding far beyond black holes alone. The universe repeatedly rewards curiosity unexpectedly. One question leads toward another. New instruments reveal entirely new realities. There is also something emotionally profound about realizing that the Milky Way contains objects like Cygnus X1 quietly hidden among ordinary stars. For thousands of years, people looked upward, imagining the heavens mostly as patterns of visible light. Modern astronomy revealed invisible complexity everywhere. Dark matter shapes galaxies. Black holes warp space-time. Neutron stars crush matter beyond atomic structure. The visible universe is only part of reality. That realization permanently changed humanity's relationship with the cosmos. The night sky no longer appears merely decorative. It became dynamic, violent, ancient, and deeply layered. And through all of this, Cygnus X1 remained historically important because it stood near the beginning of humanity's acceptance that black holes are real. Before it, black holes belonged mostly to theory. After it, they became astrophysical objects requiring serious study. Then came gravitational waves. Then event horizon imaging. Then increasingly precise relativistic measurements. The field expanded enormously. But one of the first major turning points happened because astronomers noticed a star behaving strangely inside the Swan, a wobble, an X-ray source, an invisible companion too massive to explain normally. And from those clues emerged one of the greatest scientific realizations of the modern era. The universe contains regions where gravity reshapes reality itself. Tonight, somewhere within the Milky Way, matter still spirals inward around Cygnus X1 exactly as it did long before humans evolved. The accretion disk glows in X-rays. The companion star orbits endlessly. Space-time curves around the event horizon, and on a small rocky world thousands of light years away, a species made of atoms forged inside ancient stars somehow learned enough physics to understand what was happening there. That may be the strangest and most beautiful part of the story. And so tonight, after travelling through warped space-time, collapsing stars, invisible gravity, and one of the strangest objects ever discovered, we eventually arrive somewhere unexpectedly quiet again. Back beneath the night sky. Back on Earth. Back in the small human world of soft blankets, distant traffic, ticking clocks and tired minds slowly drifting towards sleep. Meanwhile, far above us in the constellation Cygnus, Cygnus X1 continues exactly as it always has. The blue supergiant star circles endlessly beside the invisible black hole. Gas streams outward through stellar wind. Matter spirals inward through the accretion disk. X-rays erupt from plasma millions of degrees hot, and beyond the glowing chaos, the event horizon waits silently, allowing nothing that crosses it to return again. No sound reaches Earth from any of this. No warning, no visible sign in the ordinary night sky, just a distant point of light hidden among thousands of others. There is something strangely comforting about that once you sit with it long enough. Not comforting because black holes are gentle objects, they are not. Black holes are among the most extreme things nature creates. They bend space-time itself, they trap light, they challenge human intuition completely. And yet the universe contains them naturally, calmly, without drama. The galaxy does not panic about black holes existing. Stars continue orbiting, nebulae continue forming, planets continue drifting through darkness. Life continues evolving on small worlds beneath ordinary skies. In many ways, black holes remind us that the cosmos is stranger than fear alone can describe, because despite everything frightening about them, black holes are also deeply beautiful scientifically. They revealed that Einstein's relativity describes reality correctly under extreme conditions. They taught humanity how to study invisible objects indirectly. They forced astronomers to rethink stars, gravity, time, and the structure of galaxies themselves. And perhaps most importantly, they reminded us that reality extends far beyond human intuition. The universe does not become less real simply because it feels difficult to imagine. Somewhere beyond ordinary understanding, space-time curves anyway. That may actually be one of the quiet lessons hidden inside astronomy as a whole. Human beings evolved within a very narrow slice of reality. We experience moderate temperatures, weak gravity, slow motion, and ordinary scales. Our instincts work well for surviving everyday life. But the cosmos itself is vastly larger and stranger than the environments that shape those instincts. Stars explode, galaxies collide, neutron stars crush atoms, black holes trap light. And somehow, through mathematics and observation, humanity learned to uncover all of it. That achievement becomes even more extraordinary when you remember how recently it happened. For most of human history, the Milky Way appeared simply as a glowing river across the sky. People told stories about constellations, gods, animals, heroes, and wandering lights overhead. Now we know that hidden inside those same stars are stellar nurseries, supernova remnants, neutron stars, dark matter halos, and black holes feeding from companion stars. The sky did not change. Human understanding did. And perhaps that is why astronomy feels different from many other sciences emotionally. When astronomy changes, the universe itself feels transformed. The stars above you tonight are physically the same stars ancient humans saw thousands of years ago. But the meaning attached to them changed completely. The constellation Cygnus once represented a celestial swan drifting through the heavens. Now we also understand that hidden inside it lies a region where gravity reshapes time and space themselves. Both views coexist strangely. The mythological sky, the relativistic sky, human imagination and physical reality layered together. And still, even after all the equations and observations, black holes remain mysterious. That may be another reason they fascinate people endlessly. We understand enough to know they are real, enough to measure their masses and spins, enough to observe accretion disks and gravitational waves, but not enough to fully explain what happens inside them. The event horizon still hides unanswered questions from physics itself. The information paradox remains unresolved. Quantum gravity remains incomplete. Singularities remain uncertain. Black holes sit directly at the edge of human knowledge, and perhaps every generation needs some frontier like that. some place where certainty fades and curiosity continues. One especially beautiful thing about Cygnus X1 is how accidental the discovery almost feels in retrospect. Astronomers were not searching specifically for the first confirmed black hole. They noticed strange X-rays, a star wobbling oddly, an invisible companion too massive to explain comfortably. One clue led toward another, and eventually humanity realized it had found something extraordinary. That process captures science perfectly. Most discoveries do not arrive with triumphant music and flashing signs. They begin quietly. A discrepancy, a strange measurement, a small inconsistency. Reality whispering that our understanding remains incomplete. Then patient observation slowly reveals something much larger hiding underneath. There is also something wonderfully human about how reluctant many scientists initially were to accept black holes fully. Even Einstein himself resisted some implications of his own equations. Event horizons and singularities sounded too strange, too extreme, too disconnected from ordinary intuition. Then nature built them anyway. Again and again, the universe teaches the same lesson gently but firmly. Reality is not obligated to feel familiar, and yet humans continue exploring it regardless. That persistence may be our species' most impressive trait. We are tiny creatures living on a small rocky planet, orbiting an ordinary star in one galaxy among billions. And somehow, we became capable of understanding collapsed stars thousands of light years away. Not perfectly, not completely, but genuinely. We learned enough mathematics to describe curved space-time, enough engineering to launch X-ray telescopes above Earth's atmosphere, enough patience to decode invisible radiation arriving from deep space, enough imagination to accept that the universe truly contains places where light itself cannot escape. That is remarkable, especially considering we're also the same species that occasionally forgets why we entered a room halfway through walking into it. Perhaps intelligence always looks slightly messy up close. Another comforting thought about black holes is this: despite all their strangeness, they still obey physical laws. Black holes are not supernatural holes torn into reality randomly. They form naturally from stellar collapse. Their behavior follows mathematics precisely enough that scientists can predict orbital motion, accretion dynamics, gravitational lensing, and relativistic effects accurately. Even the universe's strangest objects remain part of an orderly cosmos. The laws of physics continue working. Gravity continues shaping matter. Space-time continues curving around mass. And inside that consistency, humans slowly uncover deeper understanding generation after generation. There is peace in that idea somehow. The cosmos may be vast and strange, but it is not chaos. Even black holes fit within the structure of reality. Tonight, as you rest here safely on Earth, the photons from Cygnus X1 that reach modern telescopes began travelling toward us thousands of years ago. Civilizations rose and vanished while that light crossed the galaxy. Empires formed, languages changed, entire histories unfolded beneath the stars, and still the black hole continued orbiting silently in the darkness. Space has a different relationship with time than humans do. Black holes especially remind us of this. Their existence stretches across millions or billions of years. The stellar collapse that formed Cygnus X1 happened long before human civilization existed. The system may continue evolving long after humanity itself disappears someday. Yet for one brief moment in cosmic history, conscious beings on Earth became aware of it. The universe produced a species capable of noticing black holes. That may be one of the strangest outcomes of all, and perhaps, in the end, that is the real comfort hidden inside the darkness above us. The cosmos is enormous, ancient, complicated beyond imagination, filled with objects stranger than fiction, and yet somehow, against extraordinary odds, tiny minds on a small planet learn to understand part of it. Not all of it, maybe never all of it, but enough to look toward the constellation of the Swan and recognize what hides there: an invisible collapsed star, a warped region of space-time, a place where gravity bends reality itself, and also, strangely enough, another reminder that curiosity carried humanity farther than instinct ever could. So wherever you are tonight, whether the sky above you is clear or hidden behind clouds, whether you're listening beneath city lights or somewhere quiet beneath the stars, I hope this journey through Cygnus X1 brought you a little wonder, a little calm, and perhaps a slightly different feeling when you look upward into the night. Because the darkness above us is not empty. It never was. And somewhere out there beyond the visible stars, the universe continues unfolding patiently, while Earth turns quietly beneath your window, and the long invisible story of the cosmos carries on through the night.